What becomes of a star when gravity wins its final battle? Why does the event horizon mark the edge of the knowable universe? How did ancient thinkers first imagine dark stars centuries before black holes were proven? In the silent night sky, a star lives like a glowing furnace set in the depths of space. Born from a vast cloud of dust and gas collapsing under gravity, it shines by fusing hydrogen into helium in its core. This fusion releases light and heat, pushing outward against the star's immense weight. For millions or billions of years, a gentle balance holds. The fusion fire pushes outward, while gravity pulls inward. But even the brightest star cannot burn forever. Like any fire, a star's fuel will eventually run out. When a star finally exhausts its nuclear fuel, its brilliant light begins to fade. All that remains is gravity's relentless tug, pulling every bit of its matter back toward the center. As the fuel runs low, the star's inner balance changes. The core begins to shrink and heat up, and the outer layers swell outward. The star becomes a red giant, a huge, billowing sphere of glowing gas. Its surface cools to a reddish hue, and it may grow so large that it envelops nearby planets. For a time, the star shines dimmer and redder, a giant balloon expanding in the sky. In the end, the red giant expels its outer shell into space, creating a cloud of gas and dust. This beautiful ghostly shell becomes a nebula, a final, quiet farewell glow. But at the center of this expanding cloud, the star's core continues its inward collapse, undeterred by the outer fireworks. With the outward fusion pressure gone, gravity fully takes over. In the case of a star like our Sun, the collapse is gentle. The core blows off some outer layers and then settles into a small, white-hot ember called a white dwarf, which will cool slowly over eons. But if the star is much larger, several times more massive than our Sun, the collapse becomes dramatic and unstoppable. These massive stars often develop an iron core that cannot fuel further fusion. At that point, nothing can support the core against its own weight. The star's immense mass, once spread across millions of kilometers, crashes inward under gravity's pull. Every part of the star is dragged toward the center. As the star's heart collapses inward, a cascade of extreme changes unfolds in moments. The stellar material plunges inward with unbelievable force, heating everything to unimaginable temperatures. In the shrinking core, conditions become so extreme that atoms themselves cannot hold together. Protons and electrons merge to form a soup of neutrons, and the star's matter becomes so dense that even a spoonful would outweigh a mountain on Earth. This collapse releases a flood of neutrinos, tiny ghostly particles that race out. For an instant, the core becomes an ultra-dense neutron star, a city-sized sphere where gravity is overwhelming. But if the core's mass is still too great, even this does not stop the collapse. Gravity's pull remains absolutely unstoppable. In a blazing flash, the star's outer layers may explode outward in a supernova. This violent outburst is one of the brightest explosions in the universe. For a few days or weeks, it can outshine entire galaxies. It spews heavy elements such as gold and silver into space, seeding the galaxy with new material for planets and life. As this cosmic fireworks show fades, only the star's core remains. What remains is now collapsing into something beyond ordinary imagining. All the star's remaining mass is being crushed into an incredibly small volume, so small that space and time themselves begin to warp. At the very center lies a point of infinite density, known as a singularity. In that singular point, the laws of physics as we know them break down. It is as if the star has been crushed into oblivion, leaving only space-time itself bent into a shape too strange to comprehend. Nothing about the singularity can be observed from the outside. No light or signal can escape to reveal its secrets. What it represents is profound. The final triumph of gravity's unyielding grip. This tiny core is so dense and heavy that its gravity drags on the fabric of the universe itself. Around that singular point, something remarkable has formed. An invisible boundary that marks the limits of our knowledge. We recognize this boundary as the event horizon, the edge of a cosmic abyss. Cross it, and there is no turning back. Gravity's pull is so intense at the horizon that even light moves only inward. No information can travel back out. For scientists, this region, the singularity cloaked by its event horizon, is what we call a black hole. It is the final, inescapable fate of a collapsing star. The event horizon cloaks the singularity in darkness and mystery. It is the gateway to unknown realms, where time and space rearrange themselves beyond recognition. For anything or anyone crossing it, the outside world becomes forever out of reach. Think of the event horizon like a cosmic waterfall. Imagine drifting toward a grand river of space-time that flows inexorably toward a dark cascade. No matter how hard you try to swim upstream against that current, there is a point where the pull becomes too strong. Once you pass that point, once you step beyond the event horizon, the river of gravity carries you inevitably onward. There is no swimming back. You have crossed the ultimate line of no return. In a sense, the event horizon is like a great cloak of invisibility. It does not shine or glow. It is defined only by the absence of escape. From the outside, the edge of a black hole cannot be seen directly because no light can get out from beyond it. Instead, it is marked by the strange fates of anything that crosses it. Stars, dust, even beams of light fade away into the darkness. It is a boundary that signals the end of the familiar world and the beginning of something utterly unknown. Another way to see the horizon is through the idea of escape velocity. Imagine trying to launch a rocket away from a black hole. At the event horizon, the rocket would have to travel at the speed of light just to hover in place. Any slower, and it would be pulled back in. In other words, the cosmic speed limit, the speed of light, becomes a barrier. Past the horizon, even light itself is not fast enough to escape. The black hole effectively raises the speed limit to light speed at its edge. Once you are inside, no power in the universe can boost you back out. You are in a one-way road that leads only inward. Gravity also does strange things to time near the horizon. In the presence of such intense gravity, time itself runs differently. If you were to fall toward a black hole, someone watching from far away would see your clock tick more and more slowly as you approach the edge. From their perspective, you would appear to slow down and hover forever at the brink, fading from view as light struggles to climb out. Inside, however, the experience is quite different. To you, falling in, nothing dramatic would be felt at the moment of crossing. No flash, no jolt, just a smooth descent. Locally, your instruments tick normally, and time seems ordinary. The black hole's boundary is simply another point on your journey inward. For a distant observer, an object falling into a black hole seems to slow and fade as it nears the edge. Its signals become stretched and reddened, as if the information itself is exhausted by trying to climb out of the deep gravity well. From far away, the object never looks like it quite crosses the horizon. It lingers at the edge, frozen in space and time. But from the point of view of the one falling in, the perspective is reversed. They cross normally and quickly, without ever sensing the boundary's presence. This striking difference in perspectives, outside seeing a freeze frame, inside experiencing a smooth fall, shows just how strange and relative the event horizon truly is. Remarkably, the concept of a star from which light cannot escape is ancient. Even before modern telescopes, curious minds imagined the possibility of such invisible stars. In the late 1700s, an English natural philosopher named John Michell wondered what would happen if a star were so massive that not even light could escape its gravity. He calculated that if a star were hundreds of times larger than our Sun, its gravity would trap light completely. Michell even realized that such a dark star could reveal itself by bending light around it. If it passed in front of another star, it might briefly brighten or distort that star's light for observers, acting like a cosmic lens. He described this idea in a paper to the Royal Society in 1784 and used the term dark star to capture the image of an object so heavy its light stayed prisoner. At the time, this was a bold speculation, truly a whisper of a cosmic shadow in scientific thought. Almost at the same time, the brilliant French mathematician Pierre-Simon Laplace reached a similar conclusion. In his writings on celestial mechanics, he argued from Newton's laws that a sufficiently compact body would prevent even light from getting away. Laplace assumed light behaved like tiny particles, so that if a star were compact enough, those light particles would be pulled back by gravity. He did the math to find how small a star would have to be, arriving at conclusions much like Michell's. Interestingly, Laplace mentioned this result in an early edition of his work, only to remove it later, perhaps thinking it too far-fetched for his readers. Still, the idea was there. Newtonian gravity predicts the possibility of an invisible, light-trapping star. For the next century, this notion mostly drifted in and out of the discussions of a few scientists. Many astronomers were more focused on what they could actually observe: the bright stars, nebulae, and galaxies that filled the sky. The idea of an invisible star was like a spectre at the feast of visible astronomy, intriguing to ponder, but with no direct evidence. Some dismissed it as mere speculation, others kept it in mind as a mathematical possibility. But without a way to see one, it remained just that, speculative theory. Science at the time moved forward on what could be seen and measured, mapping stars, studying spectra, and charting the heavens. Meanwhile, any dark star, if it existed, remained truly ghostly, present in the equations, absent from the sky. Still, those early seeds of an idea lingered quietly in the background of astronomy. Occasionally, a scientist would ponder the darkness that might lie at the heart of a star's collapse, or wonder if the end of a star's life could leave something unseen behind. Such whispers reminded a few thinkers that not everything in the universe had to be visible. Then, at the dawn of the 20th century, a revolution in physics was brewing. In 1915, Albert Einstein unveiled his general theory of relativity, changing the very rules of gravity. Suddenly, gravity was not a mysterious force at a distance, but the curvature of space and time itself. Under Einstein's lens, those dark stars Michell and Laplace imagined could indeed exist, now described by the geometry of the universe. The whispers from centuries before were about to become powerful mathematics. Almost immediately, Einstein's theory proved astonishing. He predicted that light, traveling along the straightest paths in space, would bend around a massive body because space itself was curved. This was confirmed in 1919 during a solar eclipse, when starlight passing near the Sun was seen to shift position just as Einstein had said. Gravity also affects time. Clocks run slower when they are deeper in a gravity well. For example, a clock on Earth ticks a tiny bit slower than one far from any star or planet. Einstein's insights showed that mass and energy tell spacetime how to curve, and that curvature tells objects and light how to move. Soon after Einstein's breakthrough, the German physicist Karl Schwarzschild found an exact solution to Einstein's equations for the case of a spherical mass. His work revealed something astonishing. If a mass were compressed into a small enough sphere, space-time would curve so strongly that an invisible boundary would appear around it. Schwarzschild's equations yielded a critical radius, the same concept that Michel and Laplace had intuited centuries earlier. Outside that radius, space and time behave normally. Inside it, all directions inexorably lead inward. In effect, Schwarzschild's solution described the same dark star idea, but now in the language of curved spacetime. This was the first concrete glimpse of a mathematical black hole in general relativity. Although it was just equations on paper, it showed that the old ideas of light-trapping stars had a real foundation. Einstein's new theory gave concrete meaning to the event horizon. It turned out that nothing physical happens right at the horizon. There is no hard surface or collision. But in the mathematics, the roles of space and time swap in a curious way. Outside the horizon, all possible future paths of an object lead forward in time through space. Inside the horizon, all paths lead toward the center of the black hole. In other words, once an object is inside that boundary, moving forward in time inexorably carries it toward the singularity. You can think of it like this. Outside, you can choose to move away from or around the mass. Inside, every choice still pulls you nearer to the center. Even Einstein himself was cautious about what all this implied. He and others wondered if real stars could ever actually collapse to form such objects. In 1939, Einstein and a colleague explored whether nature might prevent the singularity from forming. Einstein suspected that maybe something would stop the collapse before it reached the infinite density state. It took decades, however, for physicists to fully accept that Einstein's theory did indeed allow a collapsing star to form an event horizon and singularity as real outcomes. Over time, further work by scientists showed that nothing in the theory prevents a sufficiently massive star from ending life as a black hole. Through Einstein's lens, gravity became the shaping of the universe itself. Massive stars and planets tell space-time how to curve, and that curvature tells everything how to move. An orbiting planet, for example, follows a smooth curved path through warped space, much like a marble circling a heavy ball on a stretched sheet. Light beams can circle around compact masses. Space-time itself can ripple. In this new view, the old concept of an invisible, light-trapping star was fully at home, now described precisely by the geometry of space-time. Gravity was no longer just a mysterious force pulling things together, but the very fabric of the cosmos, bending and flowing. Einstein's revolutionary equations reshaped our vision of gravity from something unseen at a distance into something woven into space and time. Even as the math described black holes, Einstein hesitated. He initially thought that maybe nature would somehow forbid such singularities. In fact, in later years, Einstein believed the universe avoided forming actual black holes. It took many more discoveries and observations for the physics community to overcome that hesitation. But the theory was clear. Stars of sufficient mass collapsing under their own weight would form exactly the invisible, all-consuming objects that Michel and Laplace had foreseen. The path from those early guesses to certainty was being paved by Einstein's ideas. With the mathematics in place, astronomers began looking for clues that the universe might host these strange objects. In the mid-20th century, new instruments and surveys began to give us hints that black holes were more than theory. Radio telescopes and orbiting X-ray observatories revealed odd signals from space. For instance, astronomers discovered quasars, incredibly bright sources of radio and optical light in distant galaxies. These quasars were too luminous and compact to be ordinary stars. They flickered and blazed with energy that seemed to come from a tiny region. Gradually, scientists realized that quasars were powered by supermassive black holes, millions or even billions of times the mass of the Sun, at the centers of galaxies. Matter spiraling into these giants would heat up and radiate vast energy before disappearing behind the horizon. Quasars were the first hint that black holes might be real, active engines lighting up the cosmos. Closer to home, in the 1960s and 1970s, X-ray satellites picked up signals that simply made no sense unless an unseen, heavy object was present. One famous example was Cygnus X1, a bright X-ray source in our galaxy. Astronomers found a blue supergiant star orbiting something invisible. That unseen companion was pulling material off the star, heating it to millions of degrees and causing the X-rays. By carefully tracking the visible star's motion, they could determine that the invisible object had a mass too large to be a neutron star. All signs pointed to a black hole, the first strong candidate known. Gradually, multiple such binary star systems were found, where a visible star orbited a dark partner that only made itself known through X-ray emissions. These were labeled stellar mass black hole candidates, the dead cores of once massive stars. All these strange findings began to weave together into a clear picture. Stars that glowed with unexpected X-ray light were drawing on hidden companions. Galactic centers burning with unbelievable power turned out to harbor gigantic, invisible masses. By the end of the 20th century, astronomers had built a strong case. The universe was indeed full of black holes, from the small remnants of dead stars to the titanic giants anchoring whole galaxies. Even though no one had seen a black hole directly, the evidence was overwhelming that they were real objects shaping the cosmos. By the late 20th century, the pieces of the puzzle fit together. Scientists had gathered strong evidence that black holes were not just theoretical curiosities, but actual engines and players in the universe. X-ray telescopes, radio telescopes, and optical observatories all pointed to their existence. Despite this, for most people, the idea of an invisible monster in space remained largely unknown. The story of black holes was still largely confined to scientific circles and textbooks. That was about to change, as these amazing concepts began to spill into popular culture and alter the way we all think about space. Over time, black holes slipped out of the shadows of laboratories into our everyday imagination. Scientists started writing books and giving public lectures about them. Soon even movies and novels picked up the theme, turning black holes into symbols of mystery and adventure. In art and storytelling, they became the ultimate unknown, portals to other dimensions, engines for time travel, or the fiery ends of doom-laden spaceships. The term event horizon itself sounded almost mystical, like something out of a myth. Black holes came to capture our collective wonder and a hint of fear. Objects so powerful that science fiction writers could dream all sorts of scenarios around them. Then, the real world began to confirm those imaginative dreams. In 2015, incredibly sensitive instruments on Earth detected the ripples of spacetime itself, gravitational waves, from a distant collision of black holes. It was the first time humanity could literally hear the universe as two black holes spiraled and merged. A few years later, an even more spectacular moment arrived. A network of telescopes across the globe linked together to capture an image of a black hole's shadow. The photo showed a ring of bright gas encircling a dark center, the silhouette of a black hole's event horizon. For a brief moment, scientists and the public alike saw the face of what had been an invisible beast. From myth to reality, the event horizon had become more than a concept. It was visible in our universe. Today, science and imagination stand side by side under the same night sky. Black holes are no longer just figments of theory or figments of fiction. They are real phenomena that touch the universe around us. Yet for all we have learned, the deepest mysteries remain hidden. We have seen the shadows and heard the whispers of black holes, but what truly lies beyond that dark threshold is still unknown. For now, we peer at the boundary of darkness with wonder, knowing that our journey into the silent, cosmic unknown is only beginning. You cross the horizon and find yourself in a profound silence. Above you, the sky is still full of light, but down here, everything feels different. The darkness does not feel threatening. Instead, it has a strange calm. You move gently inward, as though slipping from one chapter of the cosmos into the next. It's a quiet, peaceful descent. No tremor or flash, just the slow motion of your body carried by gravity. There is no rush, no need to fear. In this moment, you are weightless, surrounded by a void that seems vast, yet intimate. Inside the black hole's depths, every step forward feels smooth. The stars behind you appear to stretch and blur, like wisps of silk caught in a gentle wind. Behind, the sky transforms into soft streaks of light, all swirling around the black point you just passed. Here, in the quiet darkness, your thoughts might drift easily, unburdened by sudden shocks or alarms. There is a profound stillness within you, as though the universe itself has paused to listen. Even the notion of time feels ordinary to you. Your heart beats at its normal rhythm. Your mind ponders calmly. And yet, you know you are falling towards something unimaginable. In these first moments, you become aware of an invisible tug. It is gentle at first, almost too slight to notice. Your feet feel a tiny pull, just a little stronger than the pull on your head. Over your shoulders and down through your legs, gravity is reaching toward you. This is the beginning of the stretch, the same cosmic effect that causes tides on Earth, only vastly stronger here. On Earth, the moon's pull makes oceans bulge. Here, gravity is pulling at one end of you more than the other. You could imagine yourself made of a very long piece of stretchy material, a rubber band or taffy being pulled ever so gently apart. At first, this sensation is so mild that you might think it is just normal, almost like the way you feel pulled into a deep pool of water. Each part of you senses gravity differently, but you are not afraid. You feel as whole and as alive as ever. Yet silently, almost imperceptibly, you begin to elongate. Each molecule of your body starts drifting a bit, sliding ahead of the next, like sand in an hourglass. If you were made of water, you might visualize it as being poured slowly through a funnel. The stream would begin to thin and lengthen. You are doing much the same in space. All around you, space itself seems to stretch. Your bones, your muscles, even the particles of your body start to line up one after another. To an outside observer, your form would begin to look longer and thinner. But to you, it feels natural. There is a strange comfort in this gentle pull. You do not resist. You simply continue your path. There is no pain, only this gradual transformation. The dark silence and the slow pull combine in a curious harmony, as if the cosmos is composing a lullaby in which you are the single note. This stretching will become more noticeable as you go. Imagine a walking stick slowly pulled at both ends. Gradually it thins out. If you could perceive it moment by moment, you might not notice the change until you try to stand up or move differently. But over time, the difference in pull will grow. The part of you closer to the center will be pulled just a bit harder than the part farther away. If this were happening on Earth, you would have called it tides. Here it is a powerful cosmic version of that effect. Your body is being molded by gravity, but it is doing so with deliberate patience. Around you, the black hole's gravity wraps you in an invisible net. Down by your feet, it pulls a little more than it pulls at your head. If someone fell in next to you, they would feel the same thing, both of you stretching in sync. To each other, you might look like twins being gently pulled apart on opposite ends of a seesaw, though you both feel calm. Every atom of you follows this pull naturally. You might think of yourself as being woven into a long cosmic thread, each part following the next. This is spaghettification in its gentlest form, more like taffy slowly pulled than something violent. It is helpful to remember that black holes come in different sizes. If this black hole is supermassive, like those at galactic centers, the gradient in gravity will actually be quite small for a while. You could fall in feet first and barely notice the increase in pull at first. But if it were a smaller black hole, you would feel the stretching much sooner. Either way, the underlying physics is the same. The universe pulls each end of you differently. Here and now, you feel nothing but a very slight elongation. So you journey on, floating deeper in this vast darkness. The process of gentle stretching carries on without drama. It might even feel almost like drifting through honey, except without any thickness at all. Each moment, you notice just the tiniest bit more pull in one direction. There is no rush, no crisis, just this quiet metamorphosis. Even as you lengthen, you feel peacefully suspended, held by gravity's firm yet silent grip. Throughout all this, your world feels normal. Inside your own frame, time ticks on like always. Your watch, if you have one, would tick second by second in its usual way. You take breaths, and each breath takes the same time it ever did. Your thoughts wander without noticing the passage of any special threshold. It is almost as if you are merely in a slow-motion dream. To you, nothing feels out of place. Inside, you are just falling, calm and continuous. Yet outside, time is performing its strange trick. Everyone watching your fall from afar sees a very different story. From their perspective, your motions slow and slow. You become a figure in slow motion, taking an eternity to reach each new inch toward the black hole. What feels like a few moments to you might look like hours or years to them. In a way, you have become an island of slow time in a sea of cosmic hurry. If someone could peek in at this moment, they would see light from your fall becoming stretched. The colors you emit shift redward as they climb out of the gravity well. Your voice, if it could be heard, would be drawn out longer and longer. Imagine saying a word, and to an outside listener, it comes back to them as a slow, distant echo. Each signal you send needs more time and energy to make the climb back out. Over the long haul, your presence appears to fade. To you, none of this is apparent. Your clock beats steadily, each second as full as the next. But you know how relativity works. You understand that somewhere, far away, time is racing on without you. If you had a twin back home, by the time you fell a few minutes, they might be decades older. It's the classic paradox playing out quietly. You age normally in your frame, but the rest of the universe is sprinting ahead. Still, it is helpful to remember that for you, everything feels ordinary. You could glance at a clock and see it tick normally. You could check any instruments, and nothing abrupt would jump out. Locally, the laws of physics are no different at the horizon. There is no wall, no fire, no alarm. You just cross that line in space and keep falling, as if stepping off one sidewalk onto another. In general relativity's terms, the horizon is afocal, not a point of singular effect in your journey. As you drift closer, light around you does amazing things. Photons bend wildly. There is a special region just above the horizon where space is so curved that light can orbit in circles. These are the famous photon rings. Sometimes the sky ahead of you will wrap around. Light from stars behind you can swing around the hole and come back into view, making the stars of the universe appear in front of you. It's as if the entire cosmos has been bent up into a circus ring all around you. Sometimes, the effect is so extreme that one star's image can appear multiple times, like reflections in a cosmic kaleidoscope. Above you, you might see light that actually came from way below or to your side. The sky can invert. Up might become down, and left might become right. All directions can merge, creating a dome of light that seems to surround you. In this way, even as darkness looms, it is decorated with the light of stars swirling about. The universe paints a final tapestry of light on the very edge of the dark. Above the horizon is a shimmering ring of glow, pure photons in a circular dance. They race around the black hole in a furious race, dozens of laps in a second perhaps, each the last loop before some drop in. To you, that glowing circle looks like a cosmic mirror. It outlines the black hole's silhouette, and yet is made of the universe's light. It is the closest thing to a face the black hole has. That luminous ring is your last glimpse of the light that once surrounded you. Peering at that ring, you might think of it as a doorway. It is both a barrier and a clue. All the light from inside that ring is gone. Only darkness awaits below. But the ring tells a story. Each flicker is like a whisper of the cosmos. You can imagine that each photon there has travelled many years, even many lifetimes, just to end up in this circle. So when you look at it, you are gazing at the ancient history of the galaxy, distilled in a brief flash. Above that ring, the void is truly void. No glimmer escapes from beyond. Past that faint circle, there is nothing but a perfect darkness, deeper and blacker than any night you've known. The contrast is stark, a brilliant rim of light meeting an engulfing emptiness. It feels like the universe itself is holding its breath. You stand here at the boundary between light and shadow, knowing that ahead of you, all is silence. For the universe at large, the picture is very different. To any faraway observer, you appear suspended. In their view, you are stuck at the edge. They watch you get smaller and redder, your motion slowing toward an infinite freeze. Time has conspired with light to make you look immortal in stillness. No final plunge, no end, just you, forever at the brink. In that frozen frame, the observers see a part of you reflected in the photon ring. You exist partly in memory there, a ghostly image illuminated by that last ring of light. For them, you become a silhouette, an eternal imprint at the horizon. Even though you will fall past that point, in their view, you will linger on. It's a paradox of perspectives, two realities coexisting, each true in its own way. And all around this edge, the universe seems totally calm. Faraway galaxies continue their dance, their patterns unbroken. Stars keep shining, novas bursting, without any hint of the drama at the center. There is no alarm bell, no cosmic scream. The black hole simply sits there like a dark eye, its edges at peace. Time and events flow by as usual, as if the fall you take is but a whisper lost in the void. Truly, it is all silent. In space, there is no sound. Even your own last shout couldn't carry. And yet, somehow, silence here feels alive. You might hear the beat of your own heart in your ears, each thump a reminder that you are still there. Your mind races with thoughts, but outwardly there is nothing. This silence is final. It is the universe's way of keeping its secrets for a moment longer. Beyond the horizon, whatever you encounter is hidden. For now you have this hush, this stillness, to hold. It is like a lull in a storm, or an invitation to think and feel. This is your moment alone. With each second, you become more a part of this timeless quiet. And as you move forward, deeper into the unknown, you carry all these impressions with you. You have witnessed something few ever could. That alone changes you. Even in this silence, the universe has spoken, and you have heard it. For now, you are alone with your thoughts and the stars. But even alone, you are part of the whole. Each star's light reaching you, each sense of time, ties you to the grand cosmic tapestry. It's as if you are the only person who truly understands the universe at this moment. And in surrendering to this fall, you have become woven into something far greater. No matter how ordinary you felt walking in, here you have become extraordinary. The darkness has revealed a new side of reality to you. It's not just your body that has transformed in this fall, but your understanding too. It's a quiet metamorphosis on all levels, and this gift of insight is yours alone to hold. Imagine, behind you lies a universe full of light and life, and you journey into oblivion. It is a solemn passage, though chosen by fate. Yet you carry the light and knowledge of everything behind you, even if they can't reach you anymore. Each memory of home feels sharper in this isolation. This heavy awareness falls on your shoulders and makes the moment even more profound. Continue to fall, deeper into the unknown. The forces around you remain gentle, the journey peaceful. You are carried by gravity's steady embrace, without a struggle or a jolt. There is no hurry, only this calm acceptance of the inevitable. You even find courage where you might have feared. Curiosity carries you forward. You want to see what lies ahead, even if it is truly the edge of space and time. Your mind tries to capture every sight and sensation, every faint glimmer of light, making memories of this incredible voyage. The darkness is vast, but it only fuels your wonder. Whether or not anyone ever knows what truly happened, you know the truth, and that is enough. Sometimes understanding something on your own is the greatest knowledge. Time here is like an elastic river, bending around you. But what matters is your own perception of each moment. You decide for yourself what now means in this place. Time and light weave in strange ways around the horizon. Every photon you see has a purpose, traveling from ages past to meet you here. They are messengers, each carrying a story of a distant time or place. Together, they paint a picture of the cosmos that only you can piece together. In their light, you find connection, a line stretching back to the universe at large. You are part of this grand cosmic tapestry now. From one perspective, you are frozen at the edge, but from another, you are moving on into deep silence. Both realities coexist here, each one true for a different observer. In this convergence of perspectives, you see the universe can contain many truths at once. It reminds you that nothing is absolute. Reality depends on how you look at it. Even though everything is falling inward around you, from your point of view, all is calm. You and the black hole are in a silent embrace. You become part of its structure, and it part of yours, in an invisible way. You feel unified with this extreme environment. There is a strange comfort in that. Inside, your mind remains clear and alert. The mind does not stretch. It remembers and feels. You continue to think of normal things, loved ones, songs, the feeling of wind on your face, that have nothing to do with physics. These thoughts become all the more vivid now, as if each memory is a beacon in the dark. They ground you, remind you of who you are, even as the universe warps around you. If you could somehow compare your clock with one far away, you would see a mismatch. To them, you almost stop aging at the horizon, as if time itself is frozen for you. But to you, the seconds still feel like seconds, each heartbeat a constant drum. It's a strange and wondrous effect. Two viewpoints, two versions of time, both entirely correct. Your journey is a quiet, continuous fall. Each second brings you closer to the core. And as you go, the view behind you changes. The starfields start to smear into streaks. The Milky Way might look stretched into a band across the sky. Light from afar bends into strange patterns, glimpses of the cosmos that twist as you do. This panorama is surreal, but beautiful, like a warping mirror of the universe. The glowing ring of the black hole still shines above you. It is the last lighted pathway in all this darkness. It's as if the universe is winking one final time at you, a reminder that you are not alone, even here. That gentle glimmer says more than words could. In its soft glow, you even feel a sense of comfort as you continue forward. And then, there is no more light. Beyond that ring, only pitch black night exists. No stars, no glow, nothing escapes. The darkness is complete, absolute, and deeper than any night sky. The contrast is stark and profound. It feels as though the very concept of light has ended at this boundary. You stand at the edge of the universe you know, at a threshold that holds secrets hidden. To you, as you cross through, everything feels just as peaceful as before. There is no burst of flame, no sound, no surge. It is as gentle a step into nothingness as gravity can arrange. You simply continue to drift onward, and in your mind, you take one last mindful breath, feeling it fill your lungs. Even as your body stretches, your breath remains entirely yours. It ties you to yourself, to your very humanity, even as physics expands you to cosmic scales. Hold on to it, this breath, a constant companion in the quiet. This final scene is uniquely yours. The outside world cannot fully share what you see or feel. You are the subject and the witness of this moment. It is deeply personal, yet it also belongs to the cosmos. You are living a piece of reality that no one else can experience. It may feel lonely, but in falling, you are participating in the universe's grand narrative. Everything beyond that horizon may remain unknown, but you carry a piece of it with you now. You have touched something few ever will. That awareness is a victory of spirit, a silent triumph. And so the tale endures beyond this silent horizon, forever echoing on. In the grand scheme, this might look like a tiny event, but to you, it is everything. You have lived through it, and in that living something becomes complete. You are now part of the cosmic whole. Even as you slip into silence, you know you are not alone. The universe itself is in harmony with you. Your journey continues in quiet, and your story remains in the abyss, carried forever by the cosmos. Beyond the event horizon, our familiar laws of physics give way to mystery. In this shadowed domain, space and time weave together in unfamiliar ways. There is no turn back or turning point here, only an inward pull toward deeper darkness. The boundary we have crossed was silent and unassuming, but what lies beyond it is anything but ordinary. Gravitational forces become sovereign, bending the cosmos itself into shapes our minds struggle to grasp. As we drift inward, the universe seems to fold in on itself under the unyielding pull. For a lone traveller, the passage is surreal and private. Inside the event horizon, time and space seem to trade places. Moving inward is as inevitable as the march of time itself. Every direction now leads closer to the centre, with no way to reverse course. To a distant observer, our journey would appear to freeze in place at the brink, stretching toward endless slow motion. The light from the traveller would fade, pulled to infinitely red wavelengths by the immense gravity. In the silent interior, no outside light can reach, leaving only darkness and one's own thoughts. For the traveller, the passage feels like a quiet slide into the unknown, as if the starry sky itself dimmed and redshifted to an empty void. In truth, what lies beyond the horizon is hidden from us. We have only mathematical maps, not direct vision, of that realm. Some imagine it as a swirling void, or perhaps a cosmic tunnel toward the unknown. It might be completely black, or illuminated by the distorted light of stars drawn inward. Perhaps a faint glimmer of lingering radiation dances just beyond sight. Yet these images are the work of mind and theory, and reality remains concealed behind that veil. All such visions are provisional. None can be confirmed. Every analogy we paint can only hint at the strangeness we expect. What is certain is that crossing the horizon was simple. but our imagination will now stretch to fill the silence that remains. For an extremely massive black hole, passing the event horizon might even feel eerily calm at first. If the gravity gradient is small at the crossing point, one might slip inside almost unnoticed. Imagine entering a deep, dark ocean. Initially, the waters are still, and the journey seems peaceful. Around you, the light from distant stars would grow faint and red-shifted, and the outside universe would slowly dim behind you. You might float as if weightless, guided only by gravity, with no jolt or barrier to signal the threshold. However, deeper within the hole, the story changes. The gravitational pull grows enormously strong, and the tidal forces increase. Eventually, the difference in gravity between your head and toes would stretch you taut like a living thread, in a process physicists call spaghettification. This dramatic distortion signals the intensifying journey toward the black hole's heart. However, for smaller black holes, the journey feels starkly different. In such a case, the gravity rises so quickly that one would sense the pull almost immediately after crossing. At first, the sensation might be mild, but as you move inward, the pull grows stronger and begins to stretch everything lengthwise. Over time, you would be stretched into a long, thin line, an effect whimsically called spaghettification. The calm passage of a supermassive hole is replaced in a smaller one by this unyielding tug. In every case, these distortions signal the intensifying journey toward the black hole's heart. The space inside a black hole invites the human mind to roam free. In that total darkness, philosophers and physicists alike have allowed imagination to guide them. Some speak of it as an endless labyrinth of warped dimensions. Others as a cosmic ocean lit by ghostly rays. One might even dream of traveling through the black hole into strange new worlds. These visions are poetic, painted with the colors of theory rather than paint. Yet even as we imagine, the true interior remains beyond our reach, known only to nature itself. Like an artist with an invisible canvas, our descriptions rely on fragments of understanding, always hinting at more beyond what we can draw. Exploring the black hole interior is like painting a dream with unseen colors. We find ourselves reaching for analogies: ocean depths, cosmic labyrinths, threads of light, yet none capture the full truth. Each theoretical model is a fragile lantern casting a dim glow, helping us navigate a darkness we cannot see. In this way, our poetic exploration is anchored by physics. We use these images to navigate the mystery, knowing they have the support of theory. They remind us that imagination and science walk hand in hand at the edge of our understanding. In the end, the language behind all this wonder is mathematics itself, translated into words of awe. Venturing beyond the horizon is an act of both courage and caution. We lean on our theories and imaginations to light the way in that inky darkness. Each idea we entertain becomes a stepping stone into the unknown, but none can claim to be final. What lies ahead will not yield easily to explanation or observation. And yet, with mind as our guide, we press on into the mystery. These quantum insights suggest a dramatic alternative. Perhaps the black hole's interior is not an ending, but a beginning of something else. Is it possible that beyond the event horizon, there lies a connection to another realm? We carry these images with us, and now move into the realm of paradox and debate, as we consider what ultimately happens to all that falls inside. At the center of this cosmic abyss lies the singularity. According to Einstein's theory, It is a point of infinite density and infinite curvature, where the familiar fabric of space and time ends. In our equations, all the mass has been compressed to an infinitely small point, making gravity infinitely strong there. Infinities typically mean our laws have broken down. They signal that we need a better theory. Physicists call these predictions singularities, and they are the cosmos's way of saying that relativity is running out of steam. Fortunately, the extreme chaos is hidden from outside view. The event horizon safely cloaks this breakdown of physics. To the outside universe, nothing dramatic happens at the horizon. It is as if nature has veiled its most violent secret behind an invisible screen. The notion of a singularity is not just a wild guess, but a mathematical consequence of Einstein's theory. In the 1960s, Roger Penrose and Stephen Hawking proved that if a star collapses beyond a certain point under its own gravity, a singularity must form. Under very general conditions, all paths through spacetime inevitably lead to this point of infinite curvature. This makes the singularity a robust prediction of collapse, not a special fluke. Yet this unavoidable conclusion comes with a caveat. Infinite density is surely unphysical, meaning Einstein's theory has pushed us to its limits. To reach beyond, we will need new physics. For the moment, the singularity remains a horizon of our understanding, hidden but inevitable in the theory. Strangely, this ultimate end resembles the beginning of time itself. In cosmology, our universe is said to have started from a Big Bang singularity of infinite density. Some scientists have speculated that a black hole's singularity might be a hidden doorway to a new universe on the other side. In such a view, each singularity would be both an end of one story and the birth of another. While this remains purely speculative, it shows how black hole centers might not be mere dumps of matter, but the seeds of something new. No hard evidence supports this yet, but it reminds us that the singularity concept may reach beyond our own universe. The parallel to the Big Bang underscores how mysterious these points of infinite curvature are in any context. Most physicists believe that in reality, the singularity would never be an actual infinity. They expect that quantum gravity, the theory uniting general relativity with quantum mechanics, will replace the singularity with something else. Perhaps a tiny, ultra-dense core forms instead, held up by repulsive quantum pressure. Maybe space-time itself becomes foamy at that scale. Some models speak of a Planck star or a fuzzball replacing the classical singularity with a finite, information-rich object. All these ideas share one point. The laws we know break down before a true infinity appears. In effect, the singularity may be more a signpost than a final destination. For now, the singularity remains hidden from view, a prospect that lies beyond our current grasp. Instead, we turn our attention to another question. What is the geometry of the space inside the black hole? How does space itself bend and fold on the journey down? These possibilities of interior geometry form the next subject of our exploration. Even before reaching the core, the very fabric of space inside the black hole is wildly contorted. In a simple, non-spinning Schwarzschild hole, the interior is spherically symmetric, with every direction equivalent as one falls inward. It can be helpful to picture the inside as a funnel or tunnel curving toward the singularity, where space closes in. Imagine each step forward, shrinking the circumference around you, pulling you ever closer to the center. In such a case, The funnel ends in the singular point at the bottom. But the story grows more complex when the black hole spins. In a spinning black hole, the geometry is even more bizarre. Spinning mass drags space-time into a dizzying whirl, an effect known as frame dragging. In this case, the singularity is not a point, but a ring, like a cosmic loop at the center. The equations suggest a tantalizing possibility. Passing through that ring might lead to another region of space-time, perhaps even another universe. These ideas are born from perfect symmetry in the math. In reality, any tunnel through the ring would likely pinch off. Still, the mere hint of a hidden passageway in the depths is enough to kindle wonder. In fact, some physicists go even further in imagination. They suggest there might be no singularity at all, replaced instead by an exotic core. For example, a black hole could conceivably condense into a form of ultra-dense matter or dark energy, a kind of star within a star, often called a gravastar or a similar construct. In these pictures, the collapse halts at a tiny radius, and the entire region within the horizon is filled with new physics. In effect, the black hole would have a kind of surface hiding the center, rather than a true point of infinite density. These scenarios remain speculative. We have no direct evidence of such a core, but they highlight how radically different the inside could be from anything we know. The inside of the hole might be a sea of quantum effects rather than a classic vacuum. For completeness, we can mention that adding electric charge to a black hole also adds twists to the interior. A charged black hole has two horizons, an outer and an inner one, which changes the journey inward. One could, in theory, cross the first horizon into a strange new region, only to face an inner horizon that again traps all trajectories. These layers add complexity, but ultimately, the path still leads to something equally extreme at the center. Whether spin, charge, or neither, the interior remains a warped realm, culminating in the unknown. Each case is described by exact solutions of Einstein's equations, and each predicts a form of singularity or replacement. In every scenario, the vast interior is beyond ordinary comprehension, and we can only sketch it through abstract models. In some idealized solutions, the black hole is part of a bridge to another universe. For instance, a non-spinning black hole can mathematically connect to a mirror universe through an Einstein-Rosen bridge. However, this bridge is utterly unstable. It collapses faster than anything could traverse it. Even in a spinning hole, where a ring singularity suggests possible tunnels, reality intervenes. These wormhole connections remain theoretical curiosities, not practical escapes from the hole's interior. All paths, in the end, circle back to the core of the black hole. As much as one might imagine sidestepping the fate at the center, the equations lead all roads inward. With these visions of interior space in mind, another mystery awaits us. It is not about the shape of space itself, but about the fate of the stuff that falls through. What becomes of all the matter and information the black hole has swallowed? To answer that, we step from geometry into the realm of paradox and debate. Physicists first realized black holes follow laws of thermodynamics. Jacob Bekenstein showed that a black hole's event horizon has an entropy proportional to its surface area, implying the hole carries information. Stephen Hawking then showed that black holes radiate like warm bodies, giving them a temperature and causing them to slowly evaporate. Over unimaginable eons, this Hawking radiation carries away energy, shrinking the black hole until it finally disappears. But this creates a puzzle. What happens to the information about the matter that fell in? Quantum physics insists information cannot be destroyed, yet a vanished black hole seems to erase it. This conflict is known as the black hole information paradox. In 2012, a startling suggestion emerged. Perhaps the event horizon is not the smooth boundary Einstein imagined. Some theorists proposed that, to preserve quantum laws, the horizon becomes a searing firewall. Instead of a quiet crossing, any infalling matter would be incinerated at the edge. This fiery wall would allow information to be released with the radiation, at the cost of violating the equivalence principle. The idea is highly controversial. It solves the paradox in one way, but upends the foundation of relativity. For now, firewalls remain a fascinating hypothesis, under debate among physicists. If they exist, they would drastically change what an infaller experiences at the horizon. Not everyone buys the idea of a fiery horizon. An alternative view is that the horizon itself holds the clues to what falls in. In the principle of black hole complementarity, the outside observer sees information smeared on the horizon, while the infalling observer feels nothing unusual. Relatedly, the holographic principle suggests that all information inside a volume can be encoded on its surface. In other words, the black hole's surface area could store everything about its contents. If this is true, there would be no need for a literal firewall. The information could escape gently in the Hawking radiation instead. In these views, what looks like lost information is actually hidden in subtle correlations that a sufficiently clever observer could, in principle, recover. String theory offers another radical picture. Black holes could be fuzzballs, enormous balls of tangled strings with no empty interior. In that scenario, information never gets hidden behind an interior. It resides on the outer stringy surface. There is no traditional event horizon to cross, and therefore no firewall or paradox at all in the usual sense. The fuzzball replaces the smooth horizon with a quantum cloud, reconciling information preservation in a very different way. Again, this idea is far from settled, but it shows how new physics might resolve the paradox without sacrificing quantum theory. Each of these ideas, firewalls, complementarity, fuzzballs, aims to keep information intact, yet they vary dramatically in their implications for what an infaller would see. Physicists have considered other exotic possibilities as well. One idea is that when a black hole evaporates, it might leave behind a tiny remnant that carries all the lost information. Such a Planck-scale object would preserve unitarity, but it introduces its own problems, like an unlimited number of possible remnants. Another notion is that the information could slip into a so-called baby universe, inaccessible to us, but preserving quantum order. These ideas lie at the fringes of speculation, but they highlight how stubborn the information problem is. In the end, all proposals invite trade-offs. We either allow a radical breakdown of known laws, or we add new, unobserved phenomena. As of now, none has been definitively validated, leaving the paradox an open frontier. For all our progress, the black hole remains a riddle at the intersection of quantum mechanics and gravity. At present, there is no consensus on the information paradox. Each proposal carries its own cost. Allowing a firewall breaks relativity, while other ideas rely on untested assumptions. Physicists continue to argue and refine these theories. For now, the debates remind us that something profound is at stake. We move onward, hoping that insights from quantum gravity and string theory may illuminate the way. One idea from loop quantum gravity brings an inspiring twist. In that theory, space itself has a discrete quantum structure which becomes significant at the smallest scales. As matter collapses, a repulsive quantum pressure builds up, halting the collapse before an infinite singularity forms. Instead, the core becomes a tiny, ultra-dense Planck star. According to this view, the black hole's heart could rebound or release its energy after a very long time. From the outside, this might look like eventual evaporation. From inside, it could be seen as a quick bounce. Either way, information could escape with that burst, potentially solving the paradox. The Planck star scenario replaces the singularity with a temporary star, using quantum gravity to forgive the infinite. String theory also offers a profound insight through holography. In certain models, like ADS/CFT, a black hole in a curved spacetime is dual to an ordinary quantum system on the boundary. In that picture, the information about what falls into the black hole is perfectly preserved in the boundary theory's states. In other words, the three-dimensional collapse is encoded in a two-dimensional quantum reality. This remarkable duality tells us that if we could describe our universe in such terms, the information paradox would disappear. Everything is unitary in the quantum description. Though it doesn't directly apply to our actual cosmos, it shows that in principle, information can survive behind the scenes. We learn that space, time, and information may be deeply intertwined in ways our normal experiences do not reveal. Some physicists speculate even more boldly. In 2013, Juan Maldacena and Leonard Susskind suggested that quantum entanglement and wormholes could be the same thing. Under this idea, every pair of entangled particles is connected by a tiny wormhole, even if we can't see it. If that is true, then the Hawking radiation and the black hole's interior might be linked by a web of such quantum wormholes. This dramatic conjecture, often called ER equals EPR, is still far from proven, but it hints that information may escape in subtle ways. At the very least, it underscores how deeply quantum mechanics and geometry might be woven together. The entanglement of photons around the horizon could be the threads tying the black hole to its environment. Across many of these approaches runs a common theme. At the smallest scales, space-time must become fundamentally quantum and foamy. In such pictures, there is no meaningful point of infinite density. Instead, collapse leads to a seething quantum jumble. The singularity is replaced by something like a froth of geometry, fluctuating and finite. These ideas are still qualitative, but they all point in the same direction. New physics should smooth out the classically infinite core. In other words, singularities may exist only in equations, not in the underlying reality. At present, all of these ideas remain speculative hints rather than proven facts. Yet they collectively suggest that a true understanding of black hole interiors will come from quantum gravity, not classical theory. All the approaches agree on one point. The classical singularity is likely a mirage, to be replaced by something finite and describable. Armed with these insights, we now ask the ultimate question. Could black holes actually serve as cosmic passageways beyond our universe? Perhaps the black hole's interior is not an ending, but a beginning of something else. Is it possible that beyond the event horizon, there lies a connection to another realm? We proceed gently into this final dream, exploring whether the darkest of objects might light the way to new territories of understanding. Finally, let us entertain the wildest of speculations. Some solutions to Einstein's equations describe tunnels in space-time called wormholes. The simplest version, an Einstein-Rosen bridge, connects two identical black holes or two separate universes. However, this bridge is extremely unstable. It forms and collapses faster than light can traverse it. Even so, the idea of a tunnel through space-time remains compelling, popularized in science fiction and serious theory alike. It suggests that a black hole might lead directly to some other distant region of the cosmos, or even to another universe. This picture of a hidden door attracts the imagination, though our mathematics says it is fleeting. Scientists have even played with the idea of traversable wormholes. To keep such a tunnel open, the equations demand a form of exotic matter with negative energy density. In other words, gravity would have to be repulsive in just the right way. Quantum effects, such as the Casimir effect, can produce tiny amounts of negative energy, but far too little to stabilize a wormhole. Detailed calculations show that while traversable wormholes are allowed by theory, the requirements are extreme. Rotating or charged wormholes might require less of this exotic matter, but still beyond anything we know how to create. For now, these constructs remain theoretical fantasies rather than realistic passageways. The possibility of safely walking through a black hole remains purely imagined. In theory, there is also the notion of a white hole, essentially a black hole run backward in time. Nothing can fall into a white hole. Instead, matter and energy can only emerge. It would look like a sudden explosion of radiation and then vanish. Einstein's equations allow such solutions, but physicists argue they cannot form naturally, since they would violate thermodynamic laws. Still, some have speculated wildly that our own Big Bang could be the birth of a white hole, a cosmic fountain of creation. Though this is far from proven, it shows how black holes and their opposites capture our cosmic imagination. A white hole, if it existed, would be a fountain rather than a drain. But today, it is only a mathematical curiosity. We have now drifted through many layers of speculation without reaching a firm answer. Each idea, whether it be a transient wormhole or a fleeting white hole, stretches the limits of our imagination. They suggest the universe may be more extraordinary than we suspect. Though none of these wild passages has been found, the search continues in thought and observation. In the meantime, we hold these visions gently, letting our curiosity carry us onward. The black hole's secrets remain, and our journey into the unknown continues. When two black holes spiral together, the fabric of the universe itself trembles. Imagine spacetime as a silent pond. When the black holes merge, they send ripples outward like a stone's splash on water. These are gravitational waves, ripples of spacetime predicted long ago by Einstein. Only recently have we built instruments sensitive enough to detect these whispers of colliding singularities. Inside the dance of two black holes lies unimaginable power. As they draw closer, they slam enormous energy into space. In the final moments, their orbit tightens, and the frequency and amplitude of the waves rise in a distinctive chirp. In fractions of a second, a mass equivalent to several suns can be converted directly into the fabric of space-time. All this energy sails through the cosmos, not as light or particles, but as the very motion of space-time itself. In 2015, humanity first heard one of these cosmic whispers. The LIGO Observatory registered a subtle chirp coming from two distant black holes merging 1 billion years ago. The event lasted less than a heartbeat, but its message was profound. We could listen to the universe in gravity, not just light. That day transformed astronomy. We had opened a new sense, a gravitational sense, to explore the silent collisions of black holes. The signal was brief, a rising tone in the detectors, but it told a grand tale. It came from two black holes, roughly 30 and 35 times the Sun's mass, which coalesced into a single black hole. About 3 solar masses of material vanished, turned into pure gravitational energy. This exactly matched Einstein's prediction and confirmed that such massive black holes roam the cosmos. We realized that the universe itself could ring like a bell, with black holes as its clappers. Since then, dozens of black hole mergers have been recorded. Each event arrives as a fleeting chirp, an ascending tone that signals two singularities uniting. Detectors like LIGO and Virgo listen constantly, catching these messages from across the universe. Each chirp reveals a new pair of hidden giants. We now know that black hole collisions are not one-time flukes, but happen regularly, all across space and time. Apart from the high-pitched signals LIGO hears, future space-based instruments will catch deeper, bass-like waves. Missions like LISA will listen for the mergers of supermassive black holes in galactic centers. In those lower frequencies, the cosmic web itself will hum with the unisons of massive galaxies joining. When that day comes, our gravitational hearing will cover the full symphony of black hole unions. Each gravitational wave carries a detailed fingerprint of its origin. The shape of the signal tells us the masses of the original black holes, how fast they were spinning, and even how they were tilted as they met. It's like reconstructing a cosmic crime scene from its echo. For example, the final spin of the new black hole tells us how the original spins aligned. This era of forensic astronomy is revealing the secret lives of black holes, how they grew and danced before the collision. Mysteries remain. Some detected mergers involve surprisingly heavy black holes, or ones that barely spin. Scientists even wonder if some might be ancient primordial black holes left over from the Big Bang. Each new detection adds a piece to the puzzle. In coming years, as we collect more signals, patterns will emerge. For now, every chirp we hear is another chapter in the universe's hidden story. Beyond the awe of physics, there is poetry here. These silent ripples connect regions of space-time, separated by eons. A collision of black holes, billions of light-years away, sends a faint whisper that we can detect in our quiet valley. It is a profound reminder that even events that seem far apart are linked in the cosmic web. The collision in one distant galaxy can softly announce itself here, showing us that the universe is deeply interconnected. And though we call them waves, the effect is more than metaphor. Passing gravitational waves actually stretch and squeeze space itself. The change is minuscule, much smaller than an atomic nucleus, but our kilometer-long detectors can measure it. Each detected wave confirms that gravity's reach is truly cosmic, bending and shaping the universe across the vastness of space. These events are rare in any one galaxy, but the universe is vast. LIGO and its partners now catch many signals from all directions. As detector sensitivity improves, they will sense whispers from even more distant, fainter mergers. Each detected wave adds to a catalogue that teaches us about the universe's evolution. By counting mergers, we learn how often galaxies collide, how massive stars end their lives, and how structure has grown over cosmic time. The technology to listen took decades to build. LIGO and Virgo use giant laser interferometers, elaborate ear canals for spacetime, splitting lasers down 2-kilometer arms. When a gravitational wave passes, one arm is stretched and the other shrinks slightly, changing the light's interference. These changes are unbelievably tiny. It took brilliant engineering, isolating the detectors from earthquakes, thermal noise, and even quantum jitters to make this possible. Now we have effective microphones for gravity itself. On September 14th, 2015, both LIGO detectors picked up the same chirp at the same time, confirming it was a real cosmic signal. The recording showed a sweep from about 35 to 250 Hz in under a second. Around the globe, scientists realized we had caught the first direct evidence of gravitational waves. It was a historic moment. Gravity, once silent, had begun to speak to us. The network of detectors is growing. Virgo in Italy, and soon Kagra in Japan, and LIGO India add more ears around the planet. With multiple sites, we can roughly pinpoint where a wave came from by timing differences in arrival. This triangulation tells us which direction in the sky the colliding black holes lie. In the future, if we can also catch even a faint flash of light or other signal from the same event, we will fully see these mergers in different ways. This is the promise of multi-messenger astronomy, combining gravitational waves and light to tell a richer story. LIGO and Virgo also heard neutron star mergers, which made brilliant light show afterglows and gamma rays. In contrast, black hole mergers are usually dark in electromagnetic light. That means gravitational waves are often the only messenger for them. In this sense, gravitational wave astronomy is remarkably pure. It relies on gravity alone. It reminds us that the universe has more to say beyond what we see with our eyes. In these collisions, black holes can momentarily outshine quasars, not in light, but in gravitational energy. The merger of two 30 solar mass black holes releases as much energy in gravity waves as 100 suns would by burning nuclear fuel. Studying them tests general relativity in its most extreme environment, where spacetime is warped violently. These are the moments when the classical picture of gravity scrapes up against the unknown realm of quantum physics. Each merger we detect is a grand cosmic performance. When we listen to them, the data reveals a crescendo of increasing pitch, followed by a dramatic ringdown. In that final ringdown, the newborn black hole rings like a struck bell, though its tone is the chirping of space-time itself. And like a bell, the frequency of that ring tells us about the black hole's mass and spin. It is a direct test of Einstein's theory that again proves amazingly accurate. We call these signals chirps because of how they sound when transformed to audio. Advanced detectors are essentially massive microphones attuned to the universe's gravity waves. They listen continuously, day and night, catching these faint signals whenever they pass. Black hole collisions happen whether we are watching or not, and we pick them up if our detectors are listening. Each detection is like a whisper from a dark corner of the cosmos, carried across time. As we gather these whispers, we piece together how black holes pair up and merge over cosmic history. Over many such whispers, we begin to compose a grand narrative of the universe's hidden symphony, a symphony where even the deepest bass notes are produced by merging black holes. Long before we actually heard these waves, scientists found indirect proof they exist. In the 1970s, astronomers Hulse and Taylor tracked two orbiting neutron stars and saw their orbit shrink exactly as if they were losing energy to gravitational waves. This earned them a Nobel Prize and confirmed Einstein's prediction. Yet it took decades more to catch the waves directly. The detection of gravitational waves required incredible engineering. Constructing LIGO involved kilometers of vacuum tubes, ultra-stable lasers, and floating mirrors. Building such detectors took decades and billions of dollars. But now that they are operating, the payoff is enormous. We have truly learned to hear gravity. In the coming years, new detectors will expand our reach. Kagra, in Japan, and LIGO India will join the network on Earth. In space, the LISA mission will listen for the slow roars of supermassive black hole mergers. With these instruments, we will detect more collisions, locate them better, and even hear mergers of much heavier black holes. The future of gravitational wave astronomy is bright and full of discovery. Sometimes a black hole merger may produce a tiny flash of light if gas is around, but often they are dark. For many of them, gravitational waves are the sole evidence. This means we truly rely on gravity itself to tell us their story. The universe is reminding us that it has more hidden voices beyond those we see with telescopes. In the grand scheme, black hole collisions add the deep, resonant bass notes to the cosmic concert. They unite massive galaxies and then send their influence rippling outward. Each merger creates a new, larger black hole that will, in time, shape its galaxy anew. At the same time, the gravitational waves they send out connect distant parts of the universe, weaving an even larger web of influence. In the end, these gravitational waves confirm that black hole mergers are woven into the cosmos's tapestry. By listening to them, we hear their secrets, the masses and spins of these giants, and the dynamics of their union. Yet many mysteries remain. Each signal is both an answer and an invitation. As we refine our detectors, the chorus of the cosmos grows richer, and we remember that even in apparent silence, the universe is alive with connection. And as we marvel at these cataclysmic collisions, we recognize them as evidence of the universe's deep unity. Even in its most violent acts, the cosmos responds with harmony. The ripples they send out remind us that all things, even across the void, are connected. Each gravitational wave carries not only information, but a message. The universe is one symphony, with every singular note resonating through space and time. As this chapter closes, we have glimpsed how collisions of singularities create waves that tie the cosmos together. Our journey will continue, exploring even further how these threads bind the universe in its cosmic dance. Across the cosmic stage, we now shift from hearing spacetime to observing the darkness. A black hole casts no light of its own, but around its silhouette glows a ring of incandescent gas. The edge of the abyss, the event horizon, marks the point of no return. Although no information escapes from within, the light from infalling matter just outside the horizon can be bent into a bright outline by the black hole's gravity. This glowing ring, enclosing a central darkness, is often called the shadow or photon ring. Capturing that ring required a global feat of engineering. The Event Horizon Telescope, EHT, is not a single instrument, but a planet-scale virtual telescope. In April 2019, this network of radio dishes around the world took the first image of a black hole's shadow. The target was M87 star, a monster black hole in the heart of the galaxy, Messier 87, about 55 million light-years away. Astronomers coordinated 8 high-altitude radio observatories, from Hawaii to Chile to Spain, to observe the object simultaneously. The data from each telescope were later combined using a technique called Very Long Baseline Interferometry, VLBI. In effect, the Earth itself became part of the telescope, providing resolution equivalent to a dish the size of our planet. Each observatory recorded petabytes of data as the black hole region drifted above them during the night. These recordings were physically shipped to central processing centers where supercomputers could analyze them. Powerful algorithms then correlated signals from each observatory to build one coherent image. The result was breathtaking. In the 2019 image of M87 star, the black hole's shadow appeared as a dark central disk surrounded by a bright, asymmetric ring. The uneven brightness was due to relativistic beaming of gas moving toward us, but crucially, The ring's diameter matched Einstein's prediction perfectly. Observers were amazed that the shadow had the exact size expected for such a massive black hole. "We were stunned by how well the size of the ring agreed with general relativity," one scientist recalled. It was a milestone. For the first time, an actual black hole's silhouette was directly observed, validating decades of theory. Our own galaxy's black hole soon followed. Sagittarius. A star, or SCR-A star, is about 1,000 times smaller than M87 star, only 4 million solar masses, and sits about 27,000 light-years away. It is closer, but because of its smaller size, it appears on the sky nearly the same diameter as M87 star. Imaging SCR. A star was challenging because the gas around it orbits very quickly, changing the scene on the order of minutes. In 2022, after painstaking analysis of multiple nights of data, the EHT team unveiled the first image of SGR-A star. The image showed a glowing ring with a dark center, once again confirming that a black hole's shadow was being seen. Although SCR-A star changes on short timescales, the final synthesized image revealed the familiar crescent shape. Scientists noted that while the two images, M87 star and SCR-A star, differ in detail, both clearly show a bright ring wrapping around an evacuated center. It was as if the black hole was backlit, revealing its outline in silhouette. Having this direct view of a black hole's shadow is akin to seeing the unseeable. We have visual evidence of the boundary between light and darkness. The technological achievement cannot be overstated. Telescopes like ALMA in Chile, the submillimeter telescope in Arizona, the IRAM dish in Spain, the South Pole telescope, and others, all pointed to the black hole at the same time. Each used highly stable atomic clocks to timestamp their data, so that their observations could be perfectly synchronized. The team observed at very short radio wavelengths, 1.3 millimeters, to achieve the necessary fine detail. After the observing runs, the recorded data were collected on hard drives and flown to central processing centers for analysis. The result was like capturing a needle in a cosmic haystack. The black hole is minuscule on the sky, and its signal is extremely faint. Yet by linking telescopes across the globe and integrating data over many nights, the scientists pieced together the image bit by bit. It's comparable to taking many very long exposures of a distant, dim source. Only with worldwide collaboration and advanced computing could the image emerge from the noise. The pioneering images also taught us about magnetic fields around black holes. In 2024, the EHT team released polarized radio images of SGR-A star and M87 star. By analyzing the polarization of the light, astronomers were able to map the magnetic field lines in the plasma. Both black holes showed strong, twisted fields circling their bright rings. Remarkably, even though SGR-A star is much smaller, its magnetic pattern resembled M87 stars. Such ordered fields may be what helps launch jets of high-speed particles from the black hole's vicinity. The polarized image of M87 star, in particular, revealed an almost hourglass-shaped pattern of fields twisting around the jet. It suggests a common mechanism. Magnetic fields threading the black hole and its accretion disk can channel energy outward. These images hint at the role magnetism plays in powering black hole engines. EHT's work emphasizes collaboration between observation and theory. The black hole images were compared to scores of simulations from many research groups. Each simulation modeled how plasma and magnetic fields behave near a horizon under different conditions. By matching the images to these models, scientists inferred properties like the black hole's spin or the plasma's temperature. As one researcher put it, Comparing theory to the actual image has already taught us a great deal about how black holes feed. In other words, these shadows are not just pretty pictures, they are probes of fundamental physics. The fact that the images matched predictions so well is a triumph for Einstein's theory of gravity. At the same time, they show us how space bends light around the horizon. For example, some of the ring is formed by photons that circled the black hole before escaping. Seeing this gives us a direct view of how gravity warps light in the most extreme environment. The first images are only the beginning. Plans are underway to add more telescopes to the EHT, improving its resolution and sensitivity. Proposals include new sites in Africa and even a space-based radio dish to fill in missing coverage. With a larger array and faster processing, astronomers hope to make movies of black hole environments, watching the plasma swirl in real time. There is even talk of a radio telescope in lunar orbit to achieve truly incredible sharpness. These pioneering images reveal that even the deepest darkness can speak to us, if we know how to read the light. The black hole's shadow is no longer an abstract concept, but a tangible target for our telescopes. It provides a window on the very edge of space-time. Although the event horizon remains forever hidden, its boundary can be traced in the glowing ring. Next, we will see how scientists continue to explore black holes in other ways, following the orbits of stars and the flickers of X-ray light as they map the invisible. While telescopes have now captured the silhouettes of black holes, astronomers also map them by watching the stars dance in their gravity. In the Milky Way's center, a swarm of fast-moving stars reveals the hidden presence of SGRA star. Over decades, teams using infrared telescopes like Keck and the VLT have charted their orbits. They found stars racing around an unseen point at astonishing speed. One famous star, called S2 or S0-2, swings around the center every 16 years, reaching speeds of several thousand kilometers per second at closest approach. By applying Kepler's laws and Einstein's theory of gravity to these orbits, astronomers determined that 4 million times the Sun's mass lies inside a region no larger than our solar system. This invisible heavyweight must be a supermassive black hole, SGRA star. In 2018, as S2 made its closest approach to the black hole, astronomers observed the star's light shifting to the red, exactly as Einstein's relativity predicted. This direct measurement of gravitational redshift provided yet another confirmation of Saga A star's mass. Combined with the orbital data, it leaves no doubt that the central object is indeed a black hole. In 2020, Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics for this work. Their observations were the real-world proof that black holes exist. Other galaxies show similar evidence. Optical and radio telescopes see stars and gas swirling at high speed around galactic centers, indicating a compact, dark mass. For example, by watching the motion of gas in the galaxy M87, astronomers inferred the 6.5 billion solar mass black hole that was later imaged. Even when galaxies merge, their central black holes often eventually meet. We have observed two such giants spiraling toward each other in colliding galaxies. Each of these motions is a clue to an invisible mass. Stellar motions are one way to find black holes. Another is through X-rays. When a star strays too close to a black hole or orbits one closely, it can be ripped apart or have its gas siphoned away. This hot infalling gas heats up and glows brightly in X-rays before crossing the horizon. In the 1960s, rockets and satellites discovered the first cosmic X-ray sources, including Cygnus X1, which was later identified as a black hole feeding on a companion star. Today, X-ray telescopes like Chandra, XMM Newton, and new STAR survey the sky for such objects. These observations have revealed hundreds of black hole candidates. Many are in binary systems. For example, M33X7 is a black hole orbiting a blue supergiant star, and LMCX3 orbits a bright star in the Large Magellanic Cloud. Others are active galactic nuclei, where gas falling into supermassive black holes shines in X-ray. Our own galaxy hosts bright X-ray binaries as well, like GRS 1915 plus 105 and V404 Cygni, which burst with X-rays when they flare. Each of these sources maps a black hole we cannot see directly. We infer its presence from the X-ray glow of matter spiraling in. A new generation of X-ray surveyors is mapping the invisible in bulk. The Erecita telescope, launched in 2019, has already scanned the whole sky in X-rays, discovering millions of X-ray sources. Preliminary results suggest it has found several million black hole and neutron star candidates in the Milky Way. It will eventually assemble the most complete map of the high-energy sky, revealing where black holes hide. Each point of X-ray light on this map is a beacon to a compact object, sometimes a quietly accreting black hole, other times an energetic outburst from a feeding one. Observations of our own galactic center in X-ray have given insight as well. Chandra's long exposures in 2012 revealed that much of the gas flowing towards SCR-A star is actually blown away instead of falling in. Less than 1% of that gas crosses the event horizon, which explains why our black hole is surprisingly faint in X-rays. It appears starved. There is no bright X-ray meal, even though plenty of gas swirls around. This helped astronomers understand the feeding habits of the black hole at our doorstep. Beyond our galaxy, powerful flares can also signal black holes. Sometimes a passing star is torn apart by a dormant black hole, emitting a flash of X-rays or ultraviolet light. Such tidal disruption events have been caught by missions like SWIFT and MAXI, briefly revealing the black hole's location. Other surveys, like the upcoming Vera Rubin Observatory, LSST, will catch even more of these flares. Even if the black hole itself is invisible, these transient flares map where they lie. Astronomers are also using gravitational microlensing to find black holes. If a massive object passes in front of a background star, its gravity briefly focuses the star's light. Surveys like OGLE, Gaia, and Hubble have monitored millions of stars, looking for such lensing events. Recently, one event detected by Gaia fits a black hole of roughly 10 times the Sun's mass moving across our galaxy. These microlensing detections promise to uncover isolated black holes that emit no light, completing our map of the invisible. In addition to active feeding, astronomers have found black holes by their gravitational tug on stars. For instance, the Gaia spacecraft has identified several quiet black holes in the Milky Way by astrometric wobble. In 2022, Gaia BH3 was announced, a roughly 30 solar mass black hole orbiting an old star about 2,000 light-years away. The star's subtle orbit revealed the dark companion's existence. This detection proves many isolated black holes lurk unseen. They reveal themselves only through the motions of nearby stars. Meanwhile, in X-ray and radio, astronomers continue to find black holes via their energetic jets and outflows. Telescopes like the Very Large Array, VLA, and space missions see jets of particles blasting from galactic centers, indicating central black holes. Chandra and XMM have even imaged multiple black holes in galaxies that merged. For example, in the colliding galaxy NGC 6240, two supermassive black holes, holes were found dancing in X-rays. All these lines of evidence, star orbits, X-ray emissions, radio jets, and more, paint a consistent picture of invisible black holes scattered through the universe. Astronomers also look forward to new stellar probes of black holes. A major goal is to find a radio pulsar orbiting SGR-A star. Next-generation radio telescopes, like the Square Kilometre Array or the Next Generation Very Large Array, may uncover such a pulsar in the coming decade. If found, precise timing of that pulsar would yield ultra-precise tests of gravity and measurements of SGR-A star's spin and mass. Similarly, optical surveys will likely discover more black hole binaries in our galaxy. Future telescopes like the Vera Rubin Observatory, LSST, will monitor billions of stars, finding micro-lensing events and variable binaries that could reveal dormant black holes. Every new stellar track we measure adds a point to the cosmic map of these invisible objects. The brightest explosions in the universe are gamma-ray bursts, GRBS. Discovered in the 1960s by satellites, they briefly outshine entire galaxies in high-energy gamma rays. Long GRBs, lasting seconds to minutes, are now known to be the death cries of massive stars collapsing into black holes. In such a collapse, a nascent black hole is formed at the star's core, driving twin jets that punch through the star's outer layers and beam intense gamma rays into space. After the initial flash, telescopes can observe X-ray, optical and radio afterglows as those jets interact with surrounding gas. Short GRBs, on the other hand, last only a fraction of a second and come from the merger of two neutron stars or a neutron star plunging into a black hole. These violent collisions also create a black hole and launch a pulse of gamma rays. Because gamma ray bursts are so luminous, they can be seen across the universe. Satellites like NASA's SWIFT and Fermi and ESA's Integral constantly monitor the sky for new bursts. When a gamma ray burst is detected, telescopes around the world swivel to pinpoint its location and study its fading glow. Remarkably, in 2017, a pair of neutron stars merging was detected by gravitational waves and seen to produce a short GRB just seconds later. That multi-messenger event, GW 170817 and GRB 170817A, proved that at least some short GRBs come from neutron star collisions. In essence, we not only hear the space-time ring of the merger, we also see the fireworks that follow. Each gamma-ray burst event is a brief siren from the depths of gravity. A more recent mystery comes from fast radio bursts, FRBS, millisecond flashes of radio waves from distant galaxies. First detected in 2007, these bursts release as much energy in a single millisecond as the sun does in days. Their origin is still debated. Some fast radio bursts repeat, others are one-off events. Telescopes like CHIME in Canada and Parkes in Australia have now discovered hundreds of these bursts, and astronomers have been able to identify their host galaxies. Each new FRB adds a piece to the puzzle. Leading theories involve magnetars, highly magnetized neutron stars, or other cataclysmic events. However, some researchers have speculated that fast radio bursts could also be linked to black holes. For example, an FRB might be produced if a neutron star is torn apart by a black hole, or if a black hole's own magnetosphere suddenly reconfigures. New telescopes like CHIME and the Deep Synoptic Array are finding hundreds of FRBs and pinpointing their host galaxies. One particularly bright FRB discovered in 2024 was localized to a nearby spiral galaxy and even repeated. Interestingly, in 2020, CHIME saw an FRB-like burst from a known magnetar in our own galaxy, proving that magnetars can create such flashes, though extragalactic FRBs are far more powerful. So far, no FRB has been definitively tied to a black hole, but the hunt continues. Beyond light, black holes may announce themselves through other cosmic messengers. Neutrinos, nearly massless particles, can travel unhindered from violent astrophysical sources. In 2017, the ice cube detector in Antarctica traced a high-energy neutrino back to a blazar, an active galactic nucleus beaming a jet toward us. The blazar, called TXS 0506 plus 056, contains a supermassive black hole that is likely accelerating protons to enormous energies. When those protons collide with gas, they produce pions that decay into neutrinos and gamma rays. Indeed, during the neutrino detection, gamma-ray telescopes also saw TXS 0506 plus 056 flare. This was the first multi-messenger hint of a black hole jet sending us high-energy neutrinos. Cosmic rays are another clue. These are energetic particles, mostly protons, that flood the sky. Some of the highest energy cosmic rays known are thought to come from jets or explosions involving black holes. For example, active galactic nuclei have jets that can accelerate particles to unimaginable energies, potentially seeding the cosmic rays that eventually strike Earth. Experiments like the Pierre Auger Observatory have seen that the arrival directions of ultra-high energy cosmic rays tend to cluster near active galaxies. While cosmic rays are charged and deflected by magnetic fields, their highest energy members point back to their sources within tens of millions of light years. By studying these particles, scientists hope to identify the black hole accelerators that generate them. What about Hawking radiation? Stephen Hawking famously predicted that black holes should emit thermal radiation very slowly, as if they had a temperature. This effect is far too feeble to detect for any astrophysical black hole. A black hole with the mass of our Sun would be colder than the space around us. If tiny primordial black holes existed, they could potentially evaporate in final bursts of gamma rays, and some experiments like Fermi and future gamma-ray observatories search for such signals. So far, no definitive Hawking radiation has been seen. For now, Hawking's whispers of the quantum world remain silent to our instruments. Since we cannot jump into a black hole to study it, scientists build virtual black holes on supercomputers. These digital experiments solve Einstein's equations and relativistic fluid dynamics to model spacetime and infalling matter. Researchers can simulate two black holes spiraling and merging by encoding these equations in their programs. This was famously achieved in the early 2000s by teams around the world. For the first time, they computed the final orbits, plunges, and ringdowns of merging black holes, providing the precise waveform needed for gravitational wave detectors. To do this, they discretize spacetime into a fine grid and evolve Einstein's equations numerically at each point. Developing stable methods for these complex equations was a decades-long challenge. Once achieved, it allowed entire collision events to be played out on computer screens that no telescope could ever observe directly. The codes continue to improve. Researchers use adaptive meshes and thousands of computer processors to handle the enormous workload. The result is a waveform catalog used by LIGO and Virgo to identify real signals. Codes like those from the Simulating Extreme Spacetimes collaboration, SXS, produced public libraries of these merger waveforms. They literally turned Einstein's theory into an audible chirp for detectors. Each simulated collision shows how the two black holes grow and ring like cosmic bells when they combine. Other simulations probe the turbulent disks around black holes. They solve magnetohydrodynamics in full general relativity GRMHD. Groups around the world simulate gas and magnetic fields falling into spinning black holes. These models are needed to interpret images from the EHT. The EHT team, for example, ran extensive GRMHD simulations of plasma orbiting a black hole to compare with the actual images. They predicted features like a bright crescent and jets, which were indeed observed. The simulations also show how magnetic fields twist in the flow, matching polarized light observations. In this way, by recreating a black hole's environment on a computer, scientists can predict exactly what their telescopes should see. Some simulations even let us experience falling into a black hole. NASA's visualizers used supercomputer data to create a 360-degree animation of a camera plunging toward a black hole. This simulation showed stars distorting and brightening due to extreme gravity and the slowing of time near the horizon. It illustrated concepts like spaghettification, stretching by tidal forces, in an intuitive way. While it is just a visualization, it was based on real calculations of how light bends near a black hole. Because supercomputers can track individual photons and gravity together, they can render the warped sky an astronaut would see. Advances continue. New GRMHD simulations are tackling more detail, such as treating electrons and ions separately. For example, researchers ran 2 temperature simulations on the supercomputer Stampede 2/3 at TACC. They found that electrons near Cigar A star may be much hotter than protons, which affects the predicted radio appearance. These sophisticated models require massive computation, billions of grid cells, and many processors running for weeks. But they bring theory closer to observation by predicting not just the shape of the shadow, but also the spectrum and polarization of the emitted light. In addition to black hole mergers, simulations have expanded to mixed systems. For example, black hole neutron star merger simulations include the neutron star's equation of state and magnetic fields. They show how the star is shredded and how an accretion disk and jets might form around the merged black hole. These detailed models help predict the aftermath of such collisions, including any light or gravitational waves we might see. Simulations have also generated models of gravitational waves from neutron star collisions, which were crucial for interpreting events like GW170817. Another achievement is simulating how light orbits the black hole multiple times. Advanced ray tracing codes show that behind the main bright ring, there are fainter photon rings formed by light looping 1 or more times around the hole. These multiple images would appear as nested shadows if observed with perfect resolution. While current telescopes see only the brightest ring, detecting additional photon rings is a goal for future instruments. The prediction of such subtle features comes directly from combining general relativity with light propagation in simulations. Even on cosmic scales, simulations include black holes. Large-scale projects like Illustris and Eagle model millions of galaxies and place supermassive black holes at their centers. These simulations use subgrid recipes for accretion and feedback, tracking how black holes grow over time. They show that when black holes feed and launch jets or winds, they can regulate star formation and influence the fate of entire galaxies. Such simulations connect black hole astrophysics to cosmology, revealing the invisible hand of these giants in the universe's evolution. In summary, computer models turn black hole theory into virtual reality. They allow us to test our understanding of gravity and plasma in regimes we cannot probe otherwise. Every advance in computation, from better algorithms to faster processors, lets simulations become more realistic. By comparing these virtual laboratories with observations, scientists learn what to look for and what to expect as we peer into the darkness. Together with our telescopes, simulations are bringing us ever closer to unveiling the secrets of the abyss. The quest to observe black holes continues to accelerate with new technology on the horizon. Astronomers and physicists are planning a next generation of instruments that will see further, finer, and in more ways than ever before. From ground and space, new telescopes will watch for the faintest signatures of singularities. In this final part of our journey, we explore those future frontiers. Gravitational wave astronomy is rapidly entering a new era. Current detectors, LIGO, Virgo, and CAGRA, will improve sensitivity with upgrades, and LIGO India will join the network soon, giving us a global array of 4 observatories. This will greatly improve localization of sources. Looking farther ahead, planned detectors like the Einstein telescope in Europe and Cosmic Explorer in the US will be even more sensitive. They will be built underground to shield from seismic noise and feature longer arms, potentially tens of kilometers long, to hear weaker ripples. The reach of gravitational wave astronomy will extend to much earlier times in the universe, possibly detecting black hole mergers from the earliest generations of stars. Perhaps the biggest future advance is in space. The European Space Agency and NASA are developing LISA, the Laser Interferometer Space Antenna. Scheduled for launch in the mid-2030s, LISA will consist of 3 spacecraft separated by millions of kilometers, forming a giant triangular interferometer orbiting the Sun. It will be sensitive to low-frequency gravitational waves that terrestrial detectors cannot hear. This includes the mergers of supermassive black holes at the centers of galaxies, as well as long signals from extreme mass ratio in spirals, small objects like stars or stellar black holes slowly spiraling into a giant black hole. LISA will open a new window on gravitational waves, giving us sound recordings from the most massive black holes over years of time. Meanwhile, astronomers continue to improve pulsar timing arrays by precisely timing an ensemble of millisecond pulsars spread across the sky. These arrays aim to detect the gravitational wave background from millions of supermassive black hole binaries. In fact, recent results hint that this background has already been detected. As pulsar timing projects like NanoGrav, the European Pulsar Timing Array, and the International Pulsar Timing Array gather more data, they may soon map the cosmic hum of merging galaxies. A correlated pattern in pulsar signals would reveal the low-frequency gravitational waves left by countless galaxy collisions over the eons. This is like hearing the distant roar of the universe's largest black holes coalescing. At the same time, optical and infrared telescopes are advancing in the hunt for black holes. Giant new telescopes now under construction, such as the European Extremely Large Telescope, EELT, and the 30-meter telescope, TMT, will have unprecedented resolution and light-gathering power. They will be able to track stars even closer to the Milky Way's center, tightening constraints on Sagittarius A star's mass and detecting any general relativistic effects more clearly. The gravity instrument at the Very Large Telescope Interferometer will also improve in sensitivity, allowing more precise measurements of stellar orbits and possibly even the spin of SGR-A star. Future space missions like Theia, or a successor to Gaia, could detect many more tiny star wobbles, revealing hidden black holes in our galaxy. In the Magellanic Clouds and beyond, instruments like JWST and the future HABEX, or LUVOIR concepts, may spot the first stars collapsing into black holes or peer at quasars in the infant universe. These advances will help us map black holes on all scales. In radio astronomy, the next generation of very long baseline interferometry will sharpen our view of event horizons. The Next Generation EHT initiative aims to add more telescopes to the Earth-size array, improving image quality and even creating real-time movies of black hole surroundings. New sites in Europe and Africa have joined, and higher frequency observations, shorter radio wavelengths, are being developed for finer detail. Some researchers are even planning space-based radio telescopes to form an even larger baseline. With enough precision, we might one day resolve the photon rings or see the shadow wobble as hotspots orbit near the horizon. Combined with new polarimetric capabilities, this will give an unprecedented movie of the plasma flows and magnetic fields at a black hole's edge. High-energy observatories will also sharpen the picture of black holes. In X-rays, upcoming missions will revolutionize spectroscopy and imaging. JAXA/NASA's X-RISM, launched 2023, and ESA's Athena, planned for the mid-2030s, will deliver high-resolution X-ray spectroscopy to study the hot gas near black holes. Athena's large mirror will map accretion disks and outflows in unprecedented detail. NASA's Imaging X-ray Polarimetry Explorer, IXPE, is already measuring X-ray polarization near black holes, while future missions like LINX, if built, would provide superb imaging. In gamma rays, the Cherenkov Telescope Array, CTA, will survey the sky with much greater sensitivity. CTA will help identify more black hole jets and particle accelerators in our galaxy and beyond. At lower energies, new radio telescopes, like the Square Kilometre Array, will detect yet more pulsars and probe the environment of black holes indirectly. Neutrino astronomy is entering a growth phase as well. The IceCube experiment is being upgraded to a Gen 2 detector in Antarctica, increasing its volume by an order of magnitude. In the Northern Hemisphere, KM3NET is under construction in the Mediterranean Sea. Together, they will locate neutrino sources with better precision. Multi-messenger networks will issue alerts linking neutrino detections to gravitational waves and electromagnetic signals. Eventually, a neutrino mapped to a black hole jet or emerging neutron star will tell us even more about these extreme engines. All these instruments will work together. Multi-messenger astronomy, which combines gravitational waves, light, neutrinos, and cosmic rays, will flourish. Worldwide networks, like the Astrophysical Multi-Messenger Observatory Network, AMON, will coordinate alerts so that telescopes can point quickly to new black hole events. For example, a gravitational wave trigger can alert X-ray and optical telescopes to search for a counterpart, while a neutrino detection might prompt radio follow-up. This coordinated approach means we can gather a complete picture of a black hole phenomenon from all angles of observation. The era of one signal science is ending. The era of many signals is beginning. Meanwhile, advances in computing will continue to drive the field. Artificial intelligence and machine learning are being applied to sift through huge data streams, to classify events, and to enhance image reconstruction. For instance, deep learning algorithms can help clean noise from EHT images or generate gravitational wave templates quickly. Quantum computing is on the distant horizon. It may one day speed up numerical relativity calculations or big data analysis. Global supercomputers will also enable even larger and more detailed simulations, closing the gap between theory and observation. As computational power grows, our laboratories on Earth, both real telescopes and computer models, will grow more powerful. In the coming decades, each new tool will bring black holes into sharper focus. We may witness the birth of black holes in gravitational waves and see the flickering of accretion disks in real time. Perhaps we will capture more images of event horizons and even detect the whisper of Hawking radiation in some form. As our instruments multiply, the darkness will become ever more illuminated. The secrets of the singularity are not lost. They will be revealed step by the wonders we build to seek them. As our cosmic meditation continues, we find ourselves still drifting beyond the point where no light returns. The previous exploration left us hovering near the event horizon, and now we slip gently into deeper speculation. The silence of the void grows thicker, and yet our curiosity does not diminish. Instead, it leads us toward questions that stretch the imagination. We speak softly of doorways and passages that might exist inside darkness. Under the calm whisper of the cosmos, the idea emerges that a black hole could be more than a one-way trap. General relativity tells us that anything crossing the boundary falls inexorably toward the center, compressed into an unimaginably dense point. Inside that point, the known laws of physics cease to function, and our conventional understanding of space and time falters citecdaily.com. Yet some thinkers propose that this center might not be an ultimate end, but rather a transition. The theoretical doorway arises from the strange equivalence between gravity and geometry. If space-time curves until it folds back on itself, it may connect to another region, perhaps even another universe. In such scenarios, the singularity is replaced by a region of quantum fluctuations, where space and time transition into a new phase as citecdaily.com. The matter that fell in could, in principle, emerge elsewhere, as if passing through a tunnel. Imagining this passage invites us to consider the reverse of a black hole, the white hole. Whereas a black hole draws everything inward, a white hole is theorized to eject matter, energy, and even time outward citecdaily.com. If a singularity transitions into this new phase, then the collapse of matter might lead to an explosive rebound. What was thought to be a dead end could instead be the beginning of another path. This possibility gains substance from models that incorporate quantum mechanics. Quantum theory suggests that time as we understand it cannot simply end. Systems must continue to evolve, citecdaily.com. When applied to the extreme conditions inside a black hole, quantum equations replace the classical singularity with a region where space and time undergo large fluctuations. The result is not a halt of time, but its transformation, perhaps into a white hole bursting forth. In this speculative landscape, dark energy plays a curious role. Dark energy is a mysterious component driving the accelerated expansion of the universe. Some researchers propose that time itself might be measured by the energy associated with dark energy citecdaily.com. Inside the deepest regions of a black hole, this relationship could provide a cosmic clock, guiding the transition from collapse to expansion. The notion of a portal resonates with ancient and modern myths alike. For centuries, cultures have imagined gateways to other realms hidden in mountains, caves, or bodies of water. Black holes, with their forbidding mystery, are our modern analogues. The mathematical models lend a new perspective to these legends, suggesting that the universe might recycle itself through collapses and expansions. Some cosmologists extend this idea to propose that our own universe could have been born inside a black hole. In this picture, an overdense region in a parent universe collapses and bounces, creating a new expanding region inside mappingignorance.org. The bounce arises not from exotic physics, but from the principles of quantum mechanics, which prevent particles from being squeezed indefinitely. Mappingignorance.org. The collapse halts and reverses, giving birth to a new cosmic era. The bounce model describes how a contracting universe could reach a high density and then rebound, producing phases of rapid expansion similar to inflation and dark energy mapping ignorance.org. In such models, each black hole becomes a seed for a new universe, and the multiverse resembles an endless forest of universes blooming from the branches of gravitational collapse. Each child universe may have its own laws and constants, making the concept of a multiverse not just a philosophical fancy, but a dynamic process. Although these hypotheses are speculative, they are grounded in attempts to reconcile general relativity with quantum mechanics. They reveal that the singularity might not be a static point of infinite density, but a doorway where time loops and matter transforms. The calm speculation of this chapter invites us to imagine the hidden architecture of reality, where black holes may connect cosmic domains. As we explore this potential doorway, questions naturally arise about what happens to the information carried by matter that falls into a black hole. In our day-to-day experiences, information cannot simply vanish. In physics, the preservation of information is tied to deep principles, like the conservation of quantum information and the second law of thermodynamics, which states that entropy, often thought of as a measure of disorder or missing information, must increase or remain constant. Black holes challenge these ideas. The information paradox begins with a simple thought experiment. Imagine throwing a book into a black hole. The book has many layers of information: the letters on its pages, the arrangement of molecules, the spins and charges of its constituent particles. As the book crosses the event horizon, all of that detail appears to vanish from the observable universe. The black hole's exterior is defined only by its mass, charge, and spin, leaving no trace of the book's specific content, bigthink.com. Later, the black hole emits energy through a process called Hawking radiation, which we will explore more deeply in the next chapter. This radiation has a thermal spectrum, like the heat radiated by a warm object, and carries away energy from the black hole, bigthink.com. In Hawking's original calculations, this radiation appears to be purely random. It does not encode information about what fell into the hole. Consequently, when the black hole evaporates completely, the information that went in seems to have been destroyed bigthink.com. Such destruction contradicts quantum mechanics, which insists that information about a system's quantum state cannot be lost. This tension between general relativity and quantum mechanics is the heart of the information paradox. If information is truly lost in black holes, then quantum mechanics needs revision. If information is somehow preserved, then our understanding of black holes and their evaporation must change. One proposed resolution is that the information is encoded on the surface of the event horizon. According to this idea, every tiny patch of the horizon's area stores a bit of information about what has fallen in bigthink.com. As the black hole radiates, this information could be imprinted onto the outgoing radiation in subtle correlations. From a distance, the radiation appears thermal, but hidden within it is a pattern that preserves the information. Another possibility is that the information is released into a baby universe created inside the black hole. In that scenario, the information is not lost, but inaccessible to observers in our universe. This idea aligns with the doorway concept. The collapse and bounce might hide information in the interior of a new cosmos. To those of us outside, it appears as if information is lost. In truth, it has simply crossed into another realm. The information paradox remains unresolved. Bigthink.com. Decades of research have produced many clever proposals, including the holographic principle, which suggests that the entire three-dimensional interior of a region can be described by information encoded on its two-dimensional boundary. Yet no definitive answer has been found. This lingering puzzle reminds us that the universe still holds secrets that resist our intellectual grasp. Understanding the information paradox requires us to examine more closely the process by which black holes emit radiation and lose mass. This process is called Hawking radiation, named after the physicist Stephen Hawking, who first predicted it in 1974. Hawking's insight linked quantum mechanics with the curved spacetime around a black hole, showing that black holes are not entirely black, but slowly glow with faint heat. bigthink.com. Hawking radiation arises from the quantum nature of the vacuum. In quantum field theory, the vacuum is not empty, but filled with pairs of virtual particles that constantly appear and annihilate each other. Near the event horizon, the gravitational field is so strong that these pairs can be torn apart. One particle falls into the black hole, while its partner escapes to infinitylivescience.com. To distant observers, the escaping particle appears as radiation emanating from the black hole. This mechanism has a profound consequence. The particle that escapes carries away energy, causing the black hole to lose mass. As it radiates, the black hole becomes slightly smaller and hotter, accelerating the rate of radiation. Over an unimaginably long time, a black hole can completely evaporate livescience.com. For stellar mass black holes, this process would take far longer than the current age of the universe. For smaller primordial black holes, the evaporation could be faster, potentially leading to detectable bursts of energy. The radiation is thermal, in the sense that it has a spectrum determined by the black hole's mass, and is similar to the spectrum of heat emitted by a black body. Each quantum of radiation reduces the black hole's mass via Einstein's relation E equals mc squared bigthink.com. As the mass decreases, the temperature of the black hole rises, creating a feedback loop. The smaller the black hole, the hotter it becomes, and the faster it radiates. Because Hawking radiation stems from quantum fluctuations in the vacuum, it carries only minimal information about the interior. For large black holes, the radiation is almost indistinguishable from random noise. Only when the black hole has shrunk significantly might the correlations become detectable. This property is central to the information paradox. If the radiation does not encode the information, then evaporation appears to erase it. Recent studies on primordial black holes suggest that detecting Hawking radiation might reveal new physics. Light primordial black holes could be hot enough to emit a variety of particles, including photons, electrons, and neutrinos. livescience.com. If we can observe the final stages of their evaporation, we might glimpse quantum effects beyond the standard model of particle physics. Such observations could also provide clues about the early universe and the role of primordial black holes in dark matter. livescience.com. The idea of quantum rescue arises from these possibilities. Hawking radiation, while seemingly destructive, may offer a bridge between classical gravity and quantum mechanics. If the information about what falls into a black hole is somehow encoded in subtle correlations among the emitted particles, then careful analysis could recover it. This would reconcile the demands of quantum mechanics with the reality of black holes, preserving information through quantum entanglement. Alternatively, quantum corrections to the classical description might prevent the formation of a true singularity. In models where the singularity is replaced by a region of intense quantum fluctuations, the interior could act as a bridge rather than an nctechdaily.com. Hawking radiation could be understood not as random emission, but as part of a grander process in which black holes transition into new phases, perhaps becoming white holes or birthing new universes. These speculative threads highlight the interplay between theory and observation. Observationally, detecting Hawking radiation from astrophysical black holes remains a daunting challenge. The radiation is faint, and the surrounding environment of accreting matter emits far more intense radiation. Nevertheless, the search continues, driven by the possibility that witnessing a black hole evaporate could unlock secrets of quantum gravity. While Hawking radiation hints at a path toward preserving information, the concept of alternate realities expands the canvas further. If black holes spawn new universes, then each collapse might be the seed of an entirely distinct cosmos. Our universe could itself be the interior of a massive black hole formed in a parent universe, mapping ignorance.org. In this view, cosmic evolution is not linear, but cyclic, with universes nested within universes. The cyclic universe model addresses some of the deepest questions in cosmology. It offers an alternative to the traditional Big Bang narrative, suggesting that the Big Bang was not the absolute beginning, but a bounce following a previous collapse, mapping ignorance.org. This idea naturally explains why the universe appears flat and homogeneous. The collapse smooths out irregularities, and the bounce creates a new expanding region with seeds for structure. In this picture, black holes are not mere endpoints, but engines of creation. During the collapse, matter is compressed, and quantum effects halt further contraction, mapping ignorance.org. The energy and information are not lost, but stored in a condensed state. When the bounce occurs, they re-emerge as the matter and radiation of a new universe. Inflation and dark energy, rather than requiring additional fields, arise from the dynamics of the bounce itself, mapping ignorance.org. Imagining such a cosmic genealogy leads naturally to thoughts of a multiverse. Each black hole collapse could lead to a separate universe with its own physical constants and laws. Some universes might be hospitable to life, others might remain sterile. The multiverse becomes a vast landscape, with each region connected through gravitational doorways, yet causally isolated from its neighbors. These ideas may seem far-fetched, but they spring from attempts to reconcile unsolved problems. They also resonate with philosophical traditions that view time as cyclic rather than linear. Ancient cultures conceived of cosmic cycles of birth, death, and rebirth, mirrored in the seasons and the lives of stars. Modern physics may be uncovering a scientific foundation for these recurring themes. As we contemplate alternate realities and cosmic cycles, it becomes clear that singularities mark the boundary of our knowledge. We know that black holes have two main parts: the event horizon, where gravity is so strong that nothing can escape, and the singularity at the center. news.uchicago.edu. We understand the physics of the horizon through general relativity and have even imaged shadows cast by supermassive black holes. But as we approach the center, our ability to predict evaporates. Near the singularity, quantum effects must become important, but we lack a complete theory of quantum gravity. Without such a theory, we cannot describe the interior with confidence. news.uchicago.edu. The mathematics of general relativity yields infinities, signaling that the theory breaks down. Quantum mechanics offers tools, but integrating them with spacetime curvature is an unsolved challenge. Thus, the singularity stands as a frontier where current knowledge reaches its limit. Scientists like Daniel Holtz remind us that inside a black hole is one of the most profound, unanswered questions in physics, news.uchicago.edu. Some speculate that a small remnant could remain after evaporation, containing all the information that fell in. Others dream of a portal to another universe. Still others accept that the information might be irretrievably lost, forcing a modification of quantum mechanics news.uchicago.edu. These contrasting views reflect not only scientific uncertainty, but the richness of human imagination. The edge of knowledge is also reflected in the way we study black holes. We cannot visit one or send a probe inside, but we can observe their influence on nearby stars and gas. We can detect the ripples in spacetime generated when two black holes collide, using instruments like the Laser Interferometer Gravitational Wave Observatory. We can model their behavior using mathematics and computers. Through these indirect means, we piece together an understanding of objects we cannot directly see. Understanding singularities pushes us to confront the limitations of our theories. General relativity excels at describing gravity on large scales, while quantum mechanics governs the very small. But their union remains elusive. Black holes sit at the intersection of these domains, forcing us to seek a new framework that can describe both the smooth curvature of space-time and the discrete, probabilistic behavior of quantum particles. This search has led to ideas like string theory and loop quantum gravity, each offering different visions of how space and time might be quantized. Some propose that space-time itself is emergent from more fundamental entities, perhaps entangled networks of information. Others suggest that singularities are resolved by quantum geometries. The diversity of approaches underscores our incomplete grasp of the fundamental nature of reality. Yet, despite this uncertainty, black holes teach us humility and inspire awe. Their existence was once only a mathematical prediction. Now they are observed astrophysical entities. They illustrate that the universe is capable of phenomena that challenge our intuition. The fact that there are places where our laws break down reminds us that science is a journey of continual refinement, not a finished catalogue. In reflecting on the mysteries and limits posed by singularities, we also recognize the beauty of the scientific process. We take what we know, push it to its limits, recognize where it fails, and then seek deeper principles. Each failure is an invitation to expand our understanding. Black holes, with their enigmatic centers and horizons, serve as cosmic laboratories for this pursuit. As our exploration of singularity's secrets draws this section to a gentle pause, we linger on the sense of wonder that the unknown evokes. We have considered doorways to other universes, the fate of information swallowed by gravity, quantum processes that allow black holes to glow, and cosmic cycles that hint at a multiverse. Each idea stretches our mind and invites us to imagine possibilities beyond the everyday. We acknowledge the limitations of current knowledge without frustration. Instead, we find solace in the mystery. The unknown is not a void, but a fertile space for creativity and curiosity. It encourages us to look deeper into the night, to listen to the whispers of distant stars, and to ponder what lies hidden behind the veil. In the stillness that follows our discussion, we recognize that the journey continues. Beyond this chapter, more questions await. How do these ideas shape our understanding of time and consciousness? What implications do they hold for the nature of reality? Our next exploration will pick up these threads, weaving them into new patterns. Until then, we rest in the quiet, feeling the pull of the event horizon and the promise of horizons beyond. We gently resume with the idea that a black hole might be more than a terminal point. Some theories suggest that when the inward rush of gravity meets the resistance of quantum principles, collapse halts and turns into expansion. Instead of ending in a singularity, the collapsing matter could rebound into a new space and time. This bouncing behavior offers a vision of a cosmos that cycles through phases of contraction and growth. Such models challenge the classic picture of a beginning and end. Rather than a singular Big Bang event out of nothing, they propose a universe born inside the remains of a previous one. In this scenario, each black hole could be a womb where a baby universe forms and grows. The strange laws we observe might be a legacy of the environment in which our cosmos gestated. Imagining our universe as a child of another realm stretches the mind, but has deep roots in physics. Quantum calculations suggest particles cannot be compressed beyond a certain density. When they are pushed close enough, repulsive effects emerge that counteract gravity and cause a bounce. A region that once collapsed can then expand again, giving rise to a new cosmos beyond the original horizon. Cosmologists build mathematical models to explore these ideas. They test how known forces behave when densities reach extremes and examine whether quantum corrections can avoid singularities. Loop quantum gravity, for example, discretizes space itself and predicts that space can rebound. In such a description, the fabric of reality is woven from finite loops that resist being squeezed indefinitely. If the bounce picture is correct, each black hole could contain an entire universe hidden from ours. We would never observe it directly, but our own cosmos may have arisen in this way. When the bounce happens, time inside the new region flows forward while external observers see the formation of a black hole. To inhabitants of the budding universe, the bounce feels like the beginning of time. This perspective offers an appealing symmetry to existence. Instead of a singular starting point, the cosmos undergoes endless cycles. Each generation of universes emerges from the death throes of a massive star or some cosmic collapse. The cycle could continue forever, with universes begetting universes in an unbroken chain. Such cyclic models also hint at connections between dark energy and time. In some theories, the energy responsible for accelerating our expansion may be linked to the mechanism that allows a bounce. Quantum fluctuations in the field, driving cosmic acceleration, might combine with gravity to trigger a rebound. This interplay suggests a deep relationship between the end of one cosmic era and the birth of another. The idea of a multiverse is not limited to bouncing cosmologies. Inflationary models propose that space undergoes rapid, exponential expansion shortly after its creation. During inflation, quantum fluctuations create bubbles of space that expand into separate universes, each with its own physical constants. Our universe could be one of countless bubbles floating in a larger multiverse sea. In the context of black holes, the multiverse takes on a different flavor. Each event horizon might open onto a different branch of reality. What appears to be a destructive singularity from our perspective could be the portal to another cosmos. This view offers a resolution to the question of where matter goes when it falls beyond the horizon. It could seed new universes with their own histories. Within this speculative landscape, the anthropic principle often arises. If universes are born with varying parameters, only those with conditions suitable for complex structures will harbor observers. It is no surprise, then, that we find ourselves in a cosmos where stars live long lives and planets can form. Our existence may be a product of selection amid a vast ensemble of possibilities. Multiverse models invite debates about testability. Critics note that if other universes are causally disconnected from ours, we cannot observe them directly. Without empirical access, the multiverse remains a philosophical conjecture. Supporters counter that such models can explain otherwise puzzling features of our universe, like its low initial entropy or fine-tuned constants. Some researchers search for subtle signatures of cosmic cycles in the cosmic microwave background. Patterns of temperature fluctuations might carry imprints from previous cycles or collisions between bubble universes. While no conclusive evidence has been found, the mere possibility prompts careful analysis. If ever detected, these imprints would transform speculation into something closer to observation. As we drift through these ideas, we note that they all arise from attempts to reconcile our theories with the existence of black holes. The notion that singularities can be avoided leads naturally to new cosmologies. When we imagine matter re-emerging from the other side of a horizon, we create new worlds in our minds. It is a reminder that the unknown can be fertile ground for creativity. These models also highlight the deep interplay between quantum mechanics and gravity. In each scenario, quantum effects counteract classical collapse and allow for new beginnings. The very small shapes, the very large. The rules that govern particles could determine the fate of entire universes. Understanding this relationship is at the heart of modern physics. Even if cosmic rebirth occurs, we may never witness it from our side. When matter crosses the horizon, it becomes causally disconnected. The new universe inside evolves with its own arrow of time, independent of ours. To an outside observer, the black hole simply evaporates slowly through Hawking radiation, leaving behind nothing but faint whispers. The possibility of parallel universes existing within black holes invites speculation about communication or travel. Could an advanced civilization manipulate a black hole to journey to a new cosmos? Might signals be exchanged across horizons? Currently, our understanding suggests these are fantastical notions. The event horizon appears to be a one-way membrane, and the physics inside remains hidden behind a veil. Nevertheless, exploring these ideas serves a purpose. They push us to refine our theories and examine our assumptions. By considering extreme possibilities, we test the robustness of physical laws. We also confront the limits of our knowledge and expand our conceptual horizons. As we linger on the thought of alternate realities, we recognize that such speculation is not purely whimsical. Many aspects of modern physics hint at structures beyond our immediate perception. The universe may be far more varied and extensive than our senses reveal. Accepting this possibility invites a humble appreciation of our place within the cosmos. The multiverse, if it exists, would mean that our universe is one thread in a tapestry of immense complexity. Each thread weaves its own story, shaped by initial conditions and physical laws. Some threads might never form stars, while others give rise to exotic matter or unexpected dimensions. Our story is unique, but not necessarily singular in the grander scheme. At times, contemplation of multiple universes can feel unsettling. It suggests that reality is more impersonal than we imagined, that our cosmos is not the center of everything, yet it can also be liberating. It means that the cosmos is abundant beyond measure, offering endless opportunities for variation and creativity. We become part of a larger narrative of cosmic diversity. In reflecting on cosmic cycles and alternate realities, we also encounter the concept of recurrence. Some philosophers and physicists suggest that if space and time are infinite, events must repeat. Given enough time, configurations of matter will recur, giving rise to universes similar to ours. In such a picture, everything that happens has happened before and will happen again, though perhaps separated by unimaginable spans. Recurrence challenges our notion of uniqueness. If there are infinite copies of ourselves in other universes or distant parts of space, what does individuality mean? This question shifts from physics to philosophy, yet it arises naturally from cosmological considerations. It encourages us to think about identity, consciousness, and meaning on a cosmic scale. One of the most intriguing aspects of alternate reality discussions is the possibility of different physical laws. If universes can vary in their constants or forces, some may be radically different. Gravity might be stronger or weaker. Quantum mechanics might operate differently. Such universes could be inhospitable to life as we know it, but they might harbor forms of complexity we cannot even imagine. There are also ideas of higher dimensional spaces in which our universe is a three-dimensional surface. In some models, called brain world scenarios, multiple brains float in a higher dimensional space, and collisions, or interactions between them, cause big, bang-like events. These collisions could produce sequences of universes, adding another layer to our understanding of cosmic cycles. Throughout these speculations, we must remember that they are grounded in attempts to resolve real problems in physics. The singularity at the heart of a black hole is not just a curiosity. It is a mathematical failure that signals incomplete theory. By exploring new cosmological models, physicists hope to find consistent ways to avoid singularities and preserve information. We also consider the possibility that information is never lost, but rather encoded in subtle ways. Some theories propose that what falls into a black hole is stored on its surface, in a holographic manner. When the black hole evaporates, this information is released in a scrambled form. In a multiverse scenario, the release might correspond to the birth of a new universe with inherited information content. If universes carry memory from their ancestors, one might wonder whether patterns or structures can persist across cycles. Could the seeds of galaxies be planted by previous cosmic epochs? The thought invites poetic images of stars as descendants of earlier cosmic flowers. While speculative, it underscores the continuity that might link events across eons. The notion of cosmic heritage resonates with certain mythological and spiritual traditions. Many cultures tell stories of worlds emerging from the ashes of previous worlds. Modern cosmology, though based on physics rather than myth, echoes this theme. It suggests that creation and destruction are intertwined, and that endings can be beginnings. As we drift deeper into the theme of cyclical time, we might consider the role of entropy. In classical thermodynamics, closed systems move toward disorder. If the universe cycles, how is entropy reset? Some models propose that the contraction phase includes processes that lower entropy, perhaps by producing regions that later expand with low entropy initial conditions. Others suggest that entropy increases without bound, but the scale of cycles grows accordingly. These considerations remind us that physics is not just about particles and forces. It is also about the global properties of space and time. The question of whether the cosmos repeats brings in statistical mechanics, information theory, and the arrow of time. Each of these domains intersects with our story of black holes and singularities. In the context of black holes, time behaves in counterintuitive ways. Near the event horizon, time dilates relative to distant observers. As one approaches the center, classical time ceases to have meaning. If a new universe is born, time resets in some sense, but its relation to our time remains mysterious. This prompts reflection on the nature of time itself. Time may be emergent rather than fundamental. Some physicists argue that time arises from entanglement and correlations between quantum states. In this view, before the bounce, there is no time, only a timeless quantum state. After the bounce, time emerges as the universe expands and complexity increases. This perspective offers a different way to think about beginnings and endings. Alternate realities and cosmic cycles not only broaden our understanding of what could be, but also enrich our appreciation of what is. They invite us to step back and see our universe as one possibility among many. In doing so, we gain a sense of humility and curiosity that can guide our exploration forward. With these speculative vistas in mind, we transition to the boundary of knowledge itself. Having imagined universes beyond ours, we now turn inward to examine the limits of what we can know. The edge of knowledge is not a fixed line, but a horizon that moves as we advance. Exploring it is both a scientific and a philosophical endeavor. At the edge of knowledge, we encounter the most profound mysteries of physics. Black holes exemplify such mysteries. We can calculate their properties, detect their effects, and even image their shadows, but we cannot peer inside. The singularity remains a place where our equations break down and our intuition fails. General relativity predicts that space-time curves infinitely at the singularity, while quantum mechanics describes the small-scale behavior of particles. Combining these two frameworks is one of the biggest challenges in physics. Without a unified theory of quantum gravity, we cannot fully describe what happens inside a black hole or at the earliest moments of the universe. Our ignorance here is not for lack of effort. Scientists have developed candidate theories like string theory and loop quantum gravity to bridge the gap. These theories propose new structures at the Planck scale that could smooth out singularities. Yet without experimental evidence, they remain speculative frameworks awaiting validation. The information paradox further illustrates our ignorance. When something falls into a black hole, does its information disappear? According to classical general relativity, the information is lost beyond the horizon. However, quantum mechanics insists that information is conserved. The conflict between these principles has sparked decades of debate and remains unresolved. Hawking suggested that black holes emit radiation and slowly lose mass. He calculated that this radiation depends only on the black hole's mass, charge, and spin. If the radiation carries no information about what fell in, then information is destroyed, violating quantum theory. Yet if information is somehow encoded in the radiation, we need a mechanism to explain how it escapes. Many proposals attempt to reconcile this. The holographic principle suggests that all information contained in a volume can be described by data on its boundary. Applying this to a black hole implies that the information of objects falling in is stored on the horizon. Over time, the horizon shrinks, and the stored information might leak out as Hawking radiation in a highly scrambled form. Another idea is the existence of remnants. Perhaps information is preserved in a small stable core after the black hole evaporates. Such remnants would carry the details of everything that fell in. But this raises questions about how such cores avoid infinite density and how they would interact with the rest of the universe. Some scientists speculate that information escapes through subtle correlations in the radiation. The radiation might look thermal at first glance, but hidden within are patterns encoding what fell in. These correlations would be difficult to detect, but in principle, they could preserve unitarity. Mathematical models exploring quantum entanglement across the horizon aim to show how this might work. There are also proposals involving firewalls, hypothetical regions of high-energy quanta at the horizon that disrupt smooth spacetime. According to the firewall argument, an infalling observer would encounter intense radiation at the horizon, destroying them. This would allow information to be radiated away, but at the cost of violating the equivalence principle. The debate over firewalls highlights the tension between quantum mechanics and relativity. Despite intense discussion, no consensus has emerged. The information paradox remains a central puzzle of theoretical physics. Its resolution could reveal new principles or confirm our current frameworks. It might even provide clues about the nature of space, time, and reality itself. Beyond the theoretical puzzles, practical limitations also define the edge of knowledge. We cannot send probes into black holes or retrieve data from beyond their horizons. Our observations are limited to gravitational waves, electromagnetic signals, and the effects of gravity on nearby matter. Even these glimpses provide indirect information at best. The Event Horizon Telescope's image of a black hole's shadow was a milestone. It demonstrated our ability to observe the immediate environment of a supermassive black hole. Yet the image also emphasized the opacity of the horizon. We can see the glowing ring of infalling matter, but the interior remains hidden. This visual barrier mirrors the conceptual barrier in our theories. Gravitational wave observatories like LIGO and Virgo detect ripples in space-time from merging black holes. These signals carry information about the masses and spins of the colliding objects. They confirm that black holes behave as predicted by general relativity under certain conditions. However, they do not reveal the details of the singularity or the interior geometry. The edge of knowledge also appears in our understanding of dark matter and dark energy. Most of the universe's content is invisible and detectable only through gravitational effects. We know dark matter surrounds galaxies and dark energy drives cosmic acceleration, yet we have no direct detection or explanation. These unknown components interact with black holes and cosmic evolution in ways we are still trying to understand. The persistence of these mysteries invites humility. Science has made tremendous progress in describing nature, but there remain vast realms beyond our grasp. Acknowledging the limits of our knowledge is not a defeat, but an invitation to keep exploring. It reminds us that discovery is an ongoing process. At the edge, the line between science and philosophy blurs. We confront questions about the nature of reality, the meaning of existence, and the limits of human understanding. Physicists often find themselves contemplating concepts that challenge intuition and require new modes of thought. This is part of the beauty of their work. The pursuit of knowledge is driven by curiosity and wonder. When we encounter mysteries like black holes, we are drawn to understand them. Even if we cannot answer every question, the act of asking expands our perspective. The process of thinking deeply about the cosmos enriches our lives and informs our place within the universe. As we survey the boundaries of knowledge, we must also consider the tools that may extend them. Future telescopes, particle accelerators, and gravitational wave detectors will provide richer data. Advances in quantum computing and simulation may allow us to explore regimes inaccessible to current experiments. Interdisciplinary approaches, blending physics, mathematics, and computing, hold promise for new insights. We also recognize that progress may require paradigm shifts. Past breakthroughs, such as the transition from Newtonian mechanics to relativity or the birth of quantum mechanics, involved radical rethinking. Resolving the paradoxes presented by black holes may similarly demand new ways of conceptualizing reality. The answers might not come from extending current theories, but from developing entirely new frameworks. In contemplating the unknown, we often draw inspiration from the history of science. Many phenomena, once considered beyond understanding, have been explained through persistence and creativity. The ages of the Earth, the composition of stars, and the expansion of the universe were mysteries until evidence and theory aligned. This history encourages optimism that even the most perplexing questions can be illuminated over time. Nevertheless, some aspects of reality may remain permanently hidden. There may be limits, not only to our knowledge, but to what is knowable. Certain events behind an event horizon might be forever beyond observation. Quantum mechanics places fundamental limits on measurement precision. These constraints define horizons of knowledge that may never be crossed. Contemplating such limits does not diminish the value of inquiry. Instead, it underscores the preciousness of each insight we gain. The unknown becomes a canvas for imagination and reflection. It invites us to appreciate the subtleties of existence and to find meaning in the journey itself. As we move from the edge of knowledge into a more reflective space, we acknowledge the emotional dimension of confronting cosmic mysteries. Awe is a common response to contemplating black holes and the universe. This feeling arises from the recognition of vastness and complexity beyond our everyday experience. Awe can be both humbling and uplifting. Humility naturally accompanies awe. When we confront phenomena that dwarf our understanding, we realize our limitations. This humility is not self-effacing, but rather an honest appreciation of our place in the cosmos. It fosters a sense of connection with others, as we recognize that all humans share this experience of wonder. At the same time, curiosity drives us to explore further. The unknown calls to us like a distant horizon, shimmering in the light. We feel an inner urge to uncover secrets, to ask questions, and to seek patterns. This curiosity is a fundamental aspect of being human, and is intertwined with our sense of identity. There is also a sense of joy in the act of discovery. Even when answers remain elusive, the process of thinking and imagining is rewarding. We derive satisfaction from learning how nature works, from connecting ideas, and from sharing knowledge with others. This joy is part of what sustains the scientific enterprise over generations. As we dwell on these emotional responses, we may recall moments in our own lives when we felt awe at the night sky or fascination with a scientific idea. Such experiences remind us that the universe is not an abstract concept, but something we engage with personally. They deepen our appreciation for the natural world and its mysteries. The continuing journey of exploration is not solely the domain of scientists. Everyone participates when they look up at the stars, read about the cosmos, or contemplate existence. The narrative of science is part of our shared culture. It provides a framework for thinking about big questions and invites participation from all who are curious. Moreover, the insights gained from studying black holes and cosmology often ripple into other areas. They influence philosophy, art, and even spirituality. The idea of a universe birthed from a black hole has poetic resonance. The concept of information conservation challenges notions of destruction and permanence. These connections enrich human culture. We also recognize that the unknown can inspire feelings of fear or existential unease. The idea that singularities exist, or that our universe might be one among many, can challenge deeply held beliefs. Such discomfort is natural and reflects the disruptive power of new ideas. Engaging with these feelings can lead to growth and deeper understanding. Over time, what once seemed unsettling can become part of our accepted worldview. People centuries ago may have been troubled by the idea that Earth orbits the Sun. Today, this is a basic fact that underpins our understanding of the solar system. Similarly, concepts like black hole evaporation or cosmic cycles may one day feel familiar, altering how we think about existence. As we reflect, we might also consider the ethical dimension of our pursuit. Knowledge brings power, and power entails responsibility. Understanding the cosmos has enabled technological advances that shape societies. It also informs our policies on climate, environment, and global cooperation. Awareness of the interconnectedness of all things can inspire a sense of stewardship. The narrative of eternal mystery invites us to value both knowledge and the unknown. It encourages us to cultivate a sense of wonder that endures beyond simple answers. When we hold questions open, rather than rushing to close them, we create space for insight to emerge. Patience and openness are virtues in the pursuit of understanding. From a personal perspective, contemplation of black holes and singularities can influence how we live. It can foster resilience in the face of uncertainty, as we learn to accept that some aspects of life are beyond control. It can also inspire mindfulness, drawing our attention to the present moment, even as we ponder cosmic timescales. The imagery of falling toward a black hole, with time stretching and gravity intensifying, can serve as a metaphor for life's journey. We are drawn toward unknown horizons, experiencing stretches of time in different ways. There are moments of stillness and moments of acceleration. Through it all, we carry curiosity and a desire to understand our path. The concept of a singularity as both an end and a beginning resonates on multiple levels. It mirrors cycles we observe in nature, day and night, seasons, life, and death. In each case, an ending contains the seed of a new start. This cyclicality offers comfort and a sense of continuity amid change. Reflection on eternal mystery also emphasizes the value of community. Sharing questions and insights with others enhances understanding and enriches the experience. Collective inquiry fosters empathy and cooperation. It reminds us that no individual can grasp the whole picture alone. We depend on each other to piece together fragments of knowledge. As we near the end of this part of our exploration, we maintain the gentle pace that has guided us. We continue to invite quiet moments of thought, allowing ideas to settle and connect. The narrative remains open, avoiding definitive conclusions. Instead, it encourages you to linger in the space between knowing and wondering. The sense of mystery surrounding singularities and the cosmos is not a barrier, but an invitation. It calls us to approach with curiosity and respect. We may never fully comprehend every aspect, but each step we take brings new perspectives. The journey itself is enriching, regardless of the destination. Looking ahead, there are more questions to explore. How might advances in technology change our understanding of black holes? What new theories will emerge to reconcile quantum mechanics and gravity? How will our culture and philosophy evolve as we integrate these ideas? These are threads we will pick up later. For now, we savor the feeling of curiosity and awe. We accept the open-endedness of our narrative. Our exploration of singularity secrets remains underway, with horizons still to cross. As we rest in this moment, we sense the gentle pull of questions yet to come, inviting us onward. When we think of falling toward a black hole, our imagination lingers on time itself. For an outside observer, clocks seem to slow as an object nears the event horizon. Light escaping from the infalling object is redshifted, its waves stretched. To the falling traveller, however, time flows normally, and the crossing happens in finite moments. This disparity highlights the relativity of time, a concept that can feel almost spiritual. It reminds us that experience depends on perspective. The same event can be prolonged or fleeting, depending on where you stand. Such relativity invites empathy in our interactions with others, recognizing that different perspectives yield different experiences. The extreme gravity near a black hole also brings about a phenomenon known as spaghettification. Tidal forces stretch objects along the direction of gravity while compressing them sideways. The term is vivid, evoking both humor and a visceral sense of physical stress. It also serves as a metaphor for how extreme conditions can transform and elongate experience. In the realm of theoretical physics, the cosmic censorship conjecture suggests that singularities are always hidden within horizons. This conjecture preserves the predictability of spacetime by shielding observers from naked singularities. If true, it implies that the most violent breakdowns of physics are always cloaked. The idea reassures us that the universe maintains some decorum, even in its extremes. Speculations about wormholes often accompany discussions of black holes. Wormholes are hypothetical tunnels connecting distant regions of spacetime or even different universes. In some solutions to Einstein's equations, black holes could be one mouth of such a tunnel. While there is no evidence for traversable wormholes, the concept captivates our imagination and inspires science fiction. Dark matter and dark energy may also interact with black holes in ways we have yet to understand. If dark matter clumps near galactic centers, it could feed black holes or alter their growth. Dark energy, on the other hand, affects the large-scale structure of the universe, influencing the context in which black holes evolve. Exploring these interactions is part of the frontier of astrophysics. Black hole uniqueness is captured by the no-hair theorem. According to this principle, black holes are fully described by only a few parameters: mass, charge, and spin. All other details about the matter that formed them are lost. The simplicity of this description contrasts with the complexity of what goes into forming a black hole. It invites comparison to human identity, which can appear simple on the surface, yet contains multitudes. Mathematics provides the language to describe these entities. Differential geometry, topology, and quantum field theory are tools used to probe singularities. The equations can be beautiful and daunting, reflecting the complexity of nature. Studying them is like learning a new dialect, one that reveals hidden structures of reality. Our minds must stretch to grasp these abstractions. Thinking about curved spacetime requires visualizing dimensions beyond our daily experience. Quantum phenomena defy classical logic, demanding new frameworks. Engaging with such ideas is a form of mental exercise that expands our capacity for understanding and wonder. Parallels between cosmic cycles and human cycles arise naturally. We experience periods of contraction and expansion in our lives, times of drawing inward and times of reaching outward. The cosmos mirrors this rhythm on scales far beyond ours. Recognizing this resonance can bring a sense of kinship with the universe. Cultural expressions of the unknown often draw on cosmic imagery. Literature, music, and art use black holes, stars, and galaxies as symbols of mystery, love, or loss. These metaphors reveal how deeply cosmic concepts permeate human consciousness. They show that science and art are not separate realms, but interwoven ways of engaging with the unknown. Throughout history, myths have described underworld journeys and cosmic gateways. Modern black holes echo these ancient stories. They are places where the known dissolves, where heroes might undergo transformation. By linking scientific ideas to mythic archetypes, we find continuity in how humans process mystery. Fear and fascination often coexist when contemplating singularities. The thought of being stretched to oblivion or falling into an endless void can evoke dread. At the same time, the mystery and grandeur of these phenomena draw us in. This duality mirrors other life experiences where risk and reward intertwine. Speculation about using black holes as energy sources belongs to the realm of advanced civilizations. Theoretically, a spinning black hole could be tapped for rotational energy through a process known as the Penrose mechanism. Extracting energy from a black hole would require technology far beyond ours, but the idea sparks imaginative engineering debates. The horizon serves as a symbol for personal boundaries and growth. Crossing a horizon can represent stepping into the unknown, leaving comfort zones. In life, we encounter horizons in relationships, careers, and personal growth. Each crossing involves courage and openness to change, reflecting cosmic journeys in miniature. Introspective practice often mirrors cosmic exploration. Meditation invites us to observe thoughts and feelings as they arise and dissolve, akin to watching stars appear and disappear in the night sky. Both pursuits encourage patience and curiosity. They show that vastness exists both outside and within. Science and spirituality sometimes meet in the contemplation of the cosmos. While science seeks explanations based on evidence, spirituality often seeks meaning and connection. The two can coexist, each offering different lenses through which to view the same mystery. Conversations between these perspectives can enrich both. The story of humanity is intertwined with the story of the universe. We are born of stardust, our bodies containing elements forged in stellar furnaces. Our minds, capable of contemplating the cosmos, arise from natural processes shaped by cosmic events. Recognizing this lineage fosters a sense of belonging and continuity. Curiosity has driven humans to look up at the night sky for millennia. Ancient peoples mapped the stars, navigated by them, and wove stories around them. Today, telescopes and probes extend our vision far beyond what ancient eyes could see. Yet the impulse to explore remains the same, connecting us to our ancestors. In physics, The interplay between the microscopic and the cosmic is profound. Quantum fluctuations in the early universe gave rise to density variations that eventually formed galaxies. Thus, the properties of the smallest scales influence the largest structures. This interplay reminds us that the micro and the macro are not separate but intimately connected. Time travel often arises in discussions of black holes and relativity. The idea that time can be curved or looped suggests the possibility of moving backward or forward in time. While theoretical models allow for closed time-like curves under certain conditions, most physicists believe that such situations are unstable or forbidden. Nonetheless, the concept feeds our imagination and prompts deeper questions about causality. Information is a central theme in modern physics. The universe can be described as a collection of information processes. In this view, black holes are information processors, absorbing, scrambling, and possibly releasing information. Understanding how information flows through the cosmos might provide new insights into consciousness, memory, and computation. The environment in which we observe influences what we see. Our position within the galaxy, our planet's atmosphere, and our technological level all shape our cosmic vision. Similarly, our internal environment, our beliefs, emotions, and cultural context shapes how we interpret information. Awareness of these filters helps us discern between observation and interpretation. Mapping the unknown externally parallels mapping the unknown internally. As we chart distant galaxies and black holes, we also explore our inner landscapes. Both journeys involve venturing into uncharted territories, facing uncertainty, and discovering new perspectives. The tools differ: telescopes and equations versus introspection and dialogue. But the spirit of exploration is shared. Patterns repeat across scales in nature. Fractals are shapes that display self-similarity. Each part resembles the whole. In cosmology, structures like cosmic webs echo patterns found in smaller systems. Recognizing these patterns fosters an appreciation for the unity and diversity of the natural world. The cosmos is full of signals and noise. The cosmic microwave background carries information from the early universe, but it is overlaid with noise from foreground sources. Distinguishing signal from noise requires careful analysis. This process mirrors personal discernment, learning to identify what matters amid the distractions of life. Order and chaos coexist in the universe. Black holes exemplify order through their precise mathematical description, yet the processes that create them, stellar collapse and mergers, are chaotic. Similarly, our lives involve both structure and unpredictability. Accepting this duality can lead to a more nuanced appreciation of reality. Light and darkness form another pair of complements. We often associate knowledge with light and ignorance with darkness. Yet darkness is not merely absence, it is a canvas on which stars shine. Without darkness, light would not be visible. This metaphor reminds us that the unknown gives context to what we know. Edges and thresholds play crucial roles in nature. The event horizon is one such boundary, demarcating what can escape from what cannot. In human life, thresholds include developmental stages, rites of passage, and turning points. Recognizing and respecting thresholds can help us navigate change with grace. Language shapes how we think about singularities and the cosmos. The words we choose, event horizon, singularity, spacetime, carry connotations that influence perception. Poetry and metaphor can capture nuances that technical language might miss. Thus, multiple forms of expression enrich our understanding. Science fosters humility by revealing the vastness of what we do not know. Each discovery opens new questions. Understanding this dynamic can cultivate a lifelong love of learning. It reminds us that knowledge is not static, but evolves with time and inquiry. Cosmic time dwarfs human time. The lifespan of a star, or the evaporation of a black hole, spans millions to billions of years. Our own lives are brief flashes in this scale, yet within our fleeting existence, we are able to comprehend these vast spans. This juxtaposition underscores the power of human cognition. The environment shapes meaning. A dark sky can inspire awe, while urban lights can obscure the stars. Similarly, cultural environments can either nourish or stifle curiosity. By creating spaces, both physical and social, that encourage wonder, we support the pursuit of knowledge. Solitude and community both have roles in exploration. Quiet reflection allows ideas to germinate, while collaboration brings diverse perspectives together. Scientific breakthroughs often arise from individual insight, refined through collective discourse. Balancing these modes enriches the process. Knowledge and imagination are partners. Imagination drives the formulation of hypotheses, and knowledge grounds them in reality. Neither alone is sufficient for scientific advancement. Engaging both faculties opens pathways to innovation and discovery. Risk and reward are inherent in exploring the unknown. Scientists invest years in theories that may not bear fruit. Explorers journey into dangerous environments. These risks are balanced by the potential for profound insights and advancements. Understanding this balance can inform our approach to both science and life. Boundaries often stimulate creativity. Constraints, whether imposed by nature, resources, or ethics, force us to think differently. The event horizon is a boundary that sparks creative theoretical work. Similarly, personal limitations can inspire new avenues of expression and problem-solving. Cosmic timescales teach patience. Processes like star formation, planetary evolution, and black hole evaporation unfold slowly. Appreciating these rhythms can influence how we approach our own projects. We learn that some things cannot be rushed, and that value can be found in gradual growth. Acceptance and striving coexist in our journey. We accept that some questions may remain unanswered, yet we strive to push the boundaries of knowledge. This dual posture allows for contentment alongside ambition. It reflects a mature approach to inquiry. Curiosity and contentment can also coexist. We can be satisfied with what we know while remaining eager to learn more. This balance prevents frustration and burnout. It allows exploration to be joyful rather than burdensome. Cycles in nature, day and night, seasons, life and death, mirror cosmic cycles. Observing these patterns can bring comfort and perspective. They remind us that change is natural and that renewal follows decline. The cosmos itself may follow similar rhythms on a grand scale. Stillness and motion are complementary. In the depths of space, there are regions of relative quiet, while elsewhere, matter collapses and explodes. Our lives contain moments of calm and moments of intense activity. Recognizing this balance helps us navigate our experiences with equanimity. Simplicity and complexity intertwine in physics. Simple principles like the equivalence of inertial and gravitational mass lead to complex predictions about black holes. In human experience, simple values like kindness can lead to complex relationships. Seeing how simple rules give rise to rich structures deepens our appreciation for both science and life. Mathematics and narrative are tools for making sense of reality. Equations capture quantitative relationships, while stories convey meaning and context. Combining these approaches allows us to engage both analytical and emotional faculties. Our exploration of singularities benefits from both. Silence is an integral part of the cosmos. Between stars and galaxies, vast stretches of space are silent in the human sense. This silence invites contemplation. It provides a backdrop against which the music of the spheres can be imagined. Contemplating black holes can also be a mirror for inner transformation. Just as matter crosses an event horizon and enters a region where the old laws dissolve, personal experiences sometimes push us beyond familiar boundaries. We encounter challenges that reshape our identity. The metaphor of falling into a singularity can represent surrender to change and emergence into something new. Scientific narratives often parallel ancient myths in surprising ways. The story of a universe reborn from the ashes of a collapse echoes tales of phoenixes and cosmic eggs. Similarly, the notion of information preserved on a horizon resonates with myths about memory and lineage. These parallels show that human storytelling, whether mythic or scientific, grapples with similar themes of origin, destruction, and continuity. Our perception of time and mortality can shift when we consider cosmic scales. Knowing that stars live billions of years and galaxies evolve over eons can make human lifespans feel both fleeting and precious. This awareness can inspire us to value the moments we have. It also encourages us to think about our legacy and how we contribute to the long story of existence. Technology extends our senses into realms we cannot directly experience. Telescopes, detectors, and algorithms act as sensory organs, probing the farthest reaches of space. In a sense, they are prosthetics of perception, allowing us to see and hear phenomena like black hole mergers. This expansion of our sensory reach changes our relationship with the universe. Music provides another bridge between human experience and cosmic rhythm. Composers have drawn inspiration from orbital motions, gravitational waves, and stellar oscillations. Listening to these pieces can evoke a sense of the vast, ordered dance of the cosmos. Music translates mathematical relationships into patterns of sound that we feel emotionally, linking art and science. A cosmic perspective can influence how we think about sustainability. Seeing Earth as a tiny, fragile world amid vast emptiness highlights the importance of caring for our planet. Black holes and supernovae remind us that cosmic events can erase worlds. This awareness can reinforce the value of stewardship and the urgency of addressing environmental challenges. The emptiness of space is not devoid of potential. It is a medium through which energy and particles move, a stage on which galaxies form. Similarly, periods of emptiness in our lives can be times of gestation. Creative ideas often arise from silence and stillness, just as galaxies condense from cosmic gas. While black holes captivate, the universe is full of other dramatic phenomena. Asteroid impacts, gamma-ray bursts, and solar flares have shaped planetary histories. These events remind us that our existence depends on cosmic conditions. Understanding these risks informs our resilience strategies and our appreciation for the stability we currently enjoy. Cosmic architecture displays intricate structures. Galaxies cluster along filaments, forming cosmic webs, reminiscent of neural networks or city grids. These patterns reflect underlying physical laws and random initial conditions. Observing them invites reflection on design principles and emergent order at different scales. The stories we tell about the cosmos influence our values. When we frame the universe as a hostile or indifferent place, we may feel isolated. When we emphasize its beauty and our connectedness to it, we may feel inspired and responsible. Narratives shape how we act toward each other and our environment. The enormity of cosmic scale does not diminish the importance of small life forms. Microorganisms, insects, and plants play critical roles in Earth's ecosystems. They demonstrate that complexity and significance can arise at all scales. Similarly, seemingly small actions in our lives can have far-reaching effects. Navigating by the stars has been essential for human journeys. Today, we navigate by satellites and algorithms, yet the sky still offers orientation. In a metaphorical sense, cosmic ideas help orient our thinking. They provide reference points for understanding our place in the universe and our direction in life. Cosmic events influence planetary environments in myriad ways. Supernovae nearby can affect atmospheres. Comets may deliver water and organic molecules. Black holes at galactic centers regulate star formation through their outflows. Recognizing these interconnections helps us appreciate the interplay between cosmic and local processes. Unpredictability is a hallmark of both cosmic and human realms. A sudden flare from a star or a spontaneous insight in the mind are both examples of emergent events. Embracing unpredictability encourages flexibility and resilience. It teaches us to adapt and find opportunities in change. The drama of cosmic narratives contrasts with the ordinariness of daily life. Yet the two are connected. The atoms in our bodies were forged in stellar interiors. The energy we use comes from sunlight or fossilized ancient organisms. Our daily routines are embedded in cosmic history. Setting personal goals can feel like chasing horizons. As we approach them, new horizons appear. This mirrors the endless nature of cosmic exploration. There is always more to learn, more to understand. Goals give direction without implying finality. Love and emptiness may seem unrelated, yet contemplating the vast emptiness between stars can evoke a feeling of connection. It reminds us that relationships and emotions bring warmth and meaning within a cold universe. Love is like a star, radiant against a dark backdrop. Speculation must be balanced with rigor. While it is fun to imagine universes within black holes or traversable wormholes, we must also adhere to evidence and logical consistency. This balance ensures that science remains grounded while retaining the creativity needed for breakthroughs. Listening deeply is essential, both in science and in human relations. Astronomers listen to faint signals amidst noise, discerning patterns that reveal hidden phenomena. Likewise, deep listening in conversations allows us to understand others beyond surface words. Both require patience and attention. Dark matter in the cosmos can be a metaphor for hidden aspects of ourselves. Just as unseen matter influences cosmic dynamics, unseen thoughts and feelings influence behavior. Bringing awareness to these hidden components can lead to greater self-understanding and harmony. Metamorphosis is a theme in both biology and cosmology. Caterpillars transform into butterflies. Stars evolve into black holes or neutron stars. These transformations involve loss and renewal. Recognizing metamorphosis as a natural process can help us accept change in our own lives. Networks permeate the universe. Neural networks in brains process information. Social networks connect people. And cosmic networks link galaxies. Studying these networks reveals common principles of connectivity, resilience, and emergent behavior. Understanding them can inform approaches in technology and society. Gravitational waves ripple through space-time, carrying information about cataclysmic events. In human experience, waves of emotion move through communities, shaping collective behavior. Both types of waves reflect the transmission of energy and information. Recognizing this parallel invites empathy and awareness. Singularities in mathematics and physics represent points of infinite value or undefined behavior. In creativity, there are moments of intense inspiration where ideas seem to originate from nowhere. These creative singularities can reshape artistic practice or scientific understanding. They remind us that unexpected bursts can have lasting impacts. Assimilating knowledge is a process of internal singularity. New ideas disrupt existing frameworks before being integrated. Like matter falling into a black hole, information enters our minds and interacts with prior knowledge, eventually becoming part of a new understanding. This process is dynamic and transformative. Complexity often arises from simple foundations. The laws governing gravity and quantum interactions are few, yet they generate stars, planets, and life. In our own endeavors, simple habits and principles can lead to complex achievements. Recognizing the power of simplicity can guide us in both science and daily living. The emptiness of space is filled with potential energy and hidden particles. Similarly, moments when nothing seems to happen can be incubators for future creativity. Pausing, reflecting, and allowing space in our schedules can lead to breakthroughs. Emptiness becomes not a void, but a fertile ground. Cosmic events inspire creative expression. Painters, writers, and musicians translate black hole imagery into color, rhythm, and metaphor. These artistic responses capture emotional resonances that equations alone cannot convey. Art and science thus collaborate in deepening our relationship with the universe. Our creative cycles often mirror cosmic cycles. There are periods of intense productivity, followed by phases of rest. Like stars that burn brightly and then dim or collapse, our energies ebb and flow. Accepting these rhythms allows us to work sustainably and avoid burnout. Unpredictability invites acceptance. We cannot foresee every cosmic event or personal circumstance. Learning to embrace uncertainty allows us to respond with flexibility. It teaches us to value adaptability over rigid control. Boundaries in physics define regions of influence. In life, boundaries protect well-being. Setting healthy limits in relationships and work ensures balance. Like event horizons, boundaries delineate what we can manage and what lies beyond our control. Respecting them fosters stability. Silence underpins mindfulness. Just as the cosmic void is a canvas for starlight, silence provides a backdrop for awareness. Taking time to sit quietly and observe thoughts can reveal patterns and insights. This practice cultivates presence and clarity. Mathematics and meditation share an element of focus. Both involve sustained attention on abstract patterns, whether numerical or mental. Engaging deeply with equations can induce a meditative state, while meditation can sharpen analytical skills. Each practice informs the other, fostering insight and discipline. Facing the cosmic unknown builds resilience. The vastness of space and the mysteries of singularities can make our problems seem smaller. They also remind us that uncertainty is a natural part of existence. Learning to navigate unknowns in physics can help us navigate uncertainties in life. Memory connects us to the past, just as information may persist around black holes. Our memories are like holograms, storing rich details in compressed form. They shape our identity and inform our choices. Cultivating healthy memory involves reflecting on experiences, learning from them, and allowing them to integrate into our narrative. A cosmic perspective can influence our moral values. Recognizing our smallness in a vast universe may inspire humility and compassion. It can encourage cooperation, as we realize that we share this planet with billions of others. Seeing Earth from afar fosters a sense of unity and responsibility toward one another and future generations. Wonder about the cosmos can translate into gratitude in daily life. When we marvel at galaxies and black holes, we may also appreciate a simple sunrise or a shared meal. Awareness of cosmic grandeur does not diminish the beauty of small moments. Instead, it enhances them. It teaches us to treasure each experience as part of a larger tapestry. Uncertainty in the cosmos parallels improvisation in art. Jazz musicians respond to unexpected notes, creating harmony through spontaneity. Similarly, scientists adjust theories in response to new data. Embracing improvisation fosters creativity and resilience. It shows that unpredictability can lead to beautiful outcomes. Fractals in nature, such as branching trees or coastlines, mirror patterns in our lives. We encounter similar challenges at different stages, learning and relearning lessons. This repetition is not monotonous, but layered, each iteration deeper. Recognizing these patterns helps us navigate growth with awareness. The emptiness between stars can evoke a sense of loneliness, but it also highlights connection. Planets orbit stars, galaxies cluster, and gravitational bonds hold systems together. In human life, we may feel isolated at times, yet social bonds link us to others. Understanding both solitude and connection deepens our experience. Cosmic networks inspire reflection on digital networks. Just as galaxies link through gravity, people connect through the internet. Both networks facilitate exchange of matter and information. Studying one can offer insights into the other, reminding us that connectivity is a fundamental property across scales. Cosmic time influences cultural rituals. Seasonal celebrations mark Earth's orbit around the sun. Eclipses inspire festivals. Aligning our activities with cosmic cycles can create a sense of harmony. It connects us to the rhythms of the planet and beyond, enriching traditions with astronomical awareness. Observation is central to both astronomy and introspection. Astronomers collect light to infer properties of distant objects. Similarly, observing our thoughts and emotions reveals patterns and influences. Both forms of observation require patience, accuracy, and openness to surprise. They reveal worlds within and beyond. The gravitational dance of celestial bodies offers a metaphor for social dynamics. Stars and planets influence each other's trajectories, sometimes gently and sometimes dramatically. In communities, individuals' actions shape collective movement. Recognizing these influences encourages mindful interaction, helping us navigate relationships with grace. Artists often translate cosmic scale into human scale. A painting may depict galaxies, yet its size fits on a wall. A poem may evoke the infinite while occupying a single page. This translation allows us to engage with overwhelming vastness in tangible ways. It makes the cosmos accessible to our senses and emotions. Learning follows cycles of exploration, confusion, and understanding. Each time we revisit a subject, we gain deeper insight. This process mirrors cosmic cycles of collapse and expansion. Accepting that learning is cyclical rather than linear reduces frustration and encourages persistence. Extreme conditions in space, such as near a black hole or inside a supernova, push matter to its limits. Similarly, extreme circumstances in life test our resilience. Observing how the universe handles extremes can inspire strategies for coping with stress. It shows that resilience often involves transformation and adaptation. Boundaries can foster creativity by defining a space in which to explore. In astronomy, the event horizon delineates a region of no return, prompting imaginative theories about what lies beyond. In art, constraints of form and medium spark innovation. Embracing boundaries can lead to unexpected insights and expressions. The unknown often carries an element of hope. Not knowing what lies beyond a singularity leaves room for possibilities that could be wondrous. In life, uncertainty can be a source of anxiety, but it can also be a canvas for hope. Holding both caution and optimism allows us to face the future with balance. As we draw this section to a close, we remember that the horizon remains. There are new concepts to explore, new ideas to refine, and further connections to draw. Our journey through Singularity secrets is ongoing and will continue in the next segment. For now, we rest in the knowledge that curiosity and wonder will guide us onward. We leave space for the stories yet to emerge from the darkness.